My name is Richard Ferrer, and I can say I am cloud hired.
That yes, come and join and get cloud hired. I'm cloud hired.
I'm cloud hired.
I'm cloud hired.
Hey, Go Cloud Architect family. I'm cloud hired.
So, I'm cloud hired, guys.
So I'll just say I'm cloud hired.
I'm cloud hired.
I'm cloud hired thanks to Go Cloud Architects.
It worked for me, and now I'm cloud hired.
Because of Google Architect program, I am cloud hired. See!
I am cloud hired. Thank you, Mike and the GlowCloud team.
Welcome back, everyone. We are here for day 7 of the Google Professional Cloud Architect Bootcamp, taught to you by me, Mike Gibbs, as well as Leopoldo Paredes, an engineer from our team with more than 2 decades of experience. As we go through this bootcamp, I want to remind everyone that if you just found it, because YouTube just sent you an alert, you just joined us, we still have the previous 6 days that you can watch. You can go back, watch them at any time, join us today, go back and see them. And my team will drop the link to that playlist in here because I want to make sure you maximize the experience. And quite frankly, you may want to go through this content 2 or 3 times in order to pass this exam. Because when you really know the material, the Google Professional Cloud Architect exam is a very straightforward exam. It's giving you scenario types, questions, and scenario answers. It's fairly straightforward compared to some of the other exams, but is very specific to the content. So if you need the playlist, you'll be able to go back and watch this content again. Before we begin, I wanted to tell people about a couple of things that we have going on every week to assist you in your career. Tomorrow, like every Wednesday, I try to come online and answer any career questions you have. Maybe it pertains to how to get your first tech job. Maybe it's how to get your first tech job when you don't want to start at help desk, when you want to start as either a senior engineer or a solutions architect. And pretty much everybody I've started sort of as one of those type roles. What you need to do to maybe skip HR questions about that, questions on skills that you need for a certain exam, questions on how you don't have to worry about getting laid off by AI and which people do have to lay off and how you can protect yourself. Any of these career questions we answer once a week on Wednesday, and I'll be live online tomorrow at approximately at 11 a.m. Eastern time to do a career question and answer session with you all. Now, I also wanted to let everybody know that on Thursday, we have our How to Get Your First Cloud Architect Job webinar. In this webinar, we will cover any role that you desire in the architecture space: enterprise architect, security architect, AI architect, network architect. All of our team has done all these roles for the most part, and I've done most of those roles, so I'm happy to answer any of your questions on this free webinar, where we go over the skills, talk about what you actually need to know, and talk about what it takes to be great. So, that's what we'll do in that webinar, and we'll spend a good hour answering any questions you may have and how it would pertain to building your career up. Want us to check your resume, want us to think you're ready for an exam, or an interview, want a little mini interview, want me to check your gap, tell you where you need to go. We do all this free, and it's on Thursday. The last thing I wanted to really say was that we have a free ebook that my team actually wrote. And in that guideline, there's about 550 pages to help you pass that Google Professional Cloud Architect certification and exam. So, it's there. My team will drop the link of that in the chat box. Go get it. It's completely free. And one more free thing to tell you, we've got a guide on how to win the interview in this description. So please go check that out. Now, today, the way I understand is the way it's planned is, we're going to have one set of content from me. And then Leo's got a couple of labs for you. And then we've got a little more content for me. So that should be the flow for the next three, for the rest of the day. Jazz, it is great to see you. I am thrilled to see you. I haven't seen your name pop up. It was great when I met you. It's great now that you're a solutions architect, and I'm just thrilled to see you. So welcome back. I'm really, really, really happy to see you. I know your underlying name, so thanks so much. All right. So let me know that you're awake, you are alert, that you are oriented. And give me a hashtag Google Professional Cloud Architect. And let's start with the content. And today is going to be storage and databases. And actually, Leo, you want to talk about the labs real quick?
Sure, Mike. Today we have labs about how to create and attach a persistent disk to a virtual machine, how to create a cloud storage bucket, an object storage bucket, and how to host a static website in a cloud storage bucket.
That sounds kind of fun. So, and then we'll deal with some databases, which always gets into fun. So, Chris, let's begin, and we'll see you from there. Now, we're going to discuss caches and caching, and that's going to be a key component to both cloud architecture as well as the Google Professional Cloud Architect exam. So we're going to talk about what caches are. We're going to show you the various kinds of caches and explain how they can possibly work. So that's what we're really going to talk about. But caching is really an optimization technique. And what it's going to do is store frequently accessed things in memory. And we're going to do this because memory's fast, and that means we can get it real fast. So, and I'll whiteboard it out for you in a moment. A cache is going to be temporary storage, where the data is going to be there so it can be frequently accessed for a short period of time. And by getting access to the user faster, caching improves performance, and caching increases scalability by reducing the load on the servers. And there's a lot of types of caches we can talk about. Caching is going to be useful anytime you have to access something that might be frequently accessed. So just imagine if a superstar had a cat and they took a photo of themselves with the cat and tweeted it, put it on Instagram, put it on Facebook, TikTok, whatever the social media platform is your choice. Now, what if 5 million people wanted to see the picture of the cat? That'd be a lot of work on the servers, right? But what if all that information could be stored in the cache, so the server only has to deal with it a few times or once, as opposed to the millions and millions of tasks? So that's what we're going to be talking about, is caching. We'll use them for websites, we'll use them for databases, we'll use them for so many other things. So I'm going to whiteboard a cache out for you now, and then we'll talk about why we might use it and how it's going to help. So let's say I have a website. And here's my website. And on the website, there's a new web page that everybody just wants to see. And it could be an image, whatever it is. So let's say it's a big download of some superstar's cat. And what everyone wants to see is superstars cat.jpg. That's actually what's being requested from the website, the picture of the cat. Now, without caching, here's what's going to happen. Every web request will go to the website, and the website will respond to every web request. Second request comes into the website responds a second time. Third request comes to the website responds a certain time. So what you're going to deal with here is at some point we're going to run out of capacity on this website or web servers. So we could just keep adding more web servers. That is an option. But what if instead we could put a cache directly in front of the website? And we're going to talk about different kinds of caches throughout this, and content delivery network caches versus database caches, because caching is very important in cloud architecture, or any architecture for that matter, like data center. But now let's say we have the superstars cat.jpg, which is the file, and this is now going to be the cache. The way this typically works is let's say we have a user that wants the website. This is user 1. User 1 wants to see the superstar cat. User 1 goes to the area, which is the cache sitting in front of the website. The information is not yet in the cache. The cache forwards the request to the website, and then when the website responds, the cache stores that information temporarily and then sends it back to the user. Now, user 2 now requests information from that website, and it's the same superstarcat.jpg. So user 2 sends the request to the website, and the cache has the answer, and the cache answers it. User 3 now comes in for that information before the cache times out, goes to request the information, and the cache already responds. So we can have an environment where if we had 1 million users that all wanted that same thing, the cache could respond almost every time. So imagine how much smaller our web servers actually need to be, because the cache is offloading frequently accessed information. Now, if the situation was different, if the user 1, for example, let's put a couple of things that were, for example, let's make a few items here, just so you understand what happens when there's a cache miss, a cache hit versus a cache miss. And you could be tested on that in the exam, so I'm going to talk about what that is in a second. Bear with me as I draw this out. Okay, so now in this example, what we have going on is we have 3 different things coming from the web page that people are looking for. And it's not one like before. Now we've got varied traffic. So now let's pretend that none of the users actually want to receive the same information. So for example, we have user 1, and user 1 wants to see superstarscat1.jpg. User 1 sends it, it goes to the cache doesn't have it, it's called the cache miss, and then it hits the website, and then the website responds, and when the website responds, the cache stores it, and sends the information back to user 1. Now in this particular case, and for all the users in this example, user 2 now wants superstarcat.jpg2, not this one that was previously requested, but this one. So now user 2 goes and it hits the cache and it's not there. That's called the cache miss. If it was already there, it'd be called the cache hit. The cache doesn't have it, so it sends it to the website, and the website actually responds and sends it to user 2. Now in this particular example, all the users 5,000 and users 3, 4, and 5, for example, now request something. In this case, this user is requesting superstarcat3.jpg, which is different than what the previous 2 people. So now user 3 sends a request, and it goes to the cache. It's not there. It's a cache miss. It hits the website responds, and the website now responds. The information is stored in the cache, and it's sent to user 3. Now, in this particular case, where everybody wants different traffic, the cache doesn't help at all. In fact, if everybody wanted different traffic, the cache would actually make it worse by adding latency. So in architecture, we have to understand our workloads and the use. We can't just shove stuff in there because it can make it better. So that's the concept of the cache. Now I'll walk through various caching scenarios that you may have. For example, you may have a cache, and I know you do have a cache, and that you have a cache that actually sits in your computer. And it sits between your CPU and your DRAM to store frequently accessed memory. And you know what that's going to look like? It's going to look something like this. In this particular environment, you can see what you have is you've got a CPU. The CPU typically has a level 1 cache, level 2 cache, level 3 cache, and that then intercommunicates with DRAM or system memory. So you might have something like that on your computer. Now let's talk about where else we may actually want to add some caching. And then after that, we'll talk more about caches. Here's another place we might want to add caching. Let's say we have a database. So caching will help us scale databases. So now let's look at a cache in front of a database. Okay, now let's talk about database caching, and let's talk about where this can help and, of course, where it won't help. So let's say we have a database. And We'll talk later about how to scale a database because there's certain things you can do and certain things you typically can't do with database scaling. But let's at least talk about a database. So with a database, we have read load and write load. Write load is when things are written to the database, and read load is when things are pulled from the database. And we want to separate these out because when it comes to scaling databases, we're going to have to separate these. And we're also going to have read load. And why does this matter? I'll show you in a minute. So we have read load, which is pulling from the database, and we have write load, which is actually writing to the database. So at some point, we're going to run out of capability on the main database server. So if you realize that you have to read and you have to write, it's a lot of work for the database. So if reading is taking up 50% of the CPU, then the server itself only has 50% left for writing. Now, why does this matter? Well, with relational databases, with many of them, they can only write to one server. Others are different, but for many of them, we can only write to one server. So if the database has all of this read load on it, the CPU only has a capacity for 50% write. So we'll talk about things like read replicas to offload the database for information, and we'll also talk about caching. So now let's imagine we stick a cache in front of this database. And let's say in this situation that 80% of the things that are coming out of the database are the same thing. Because remember, caching helps when we're pulling the same thing, but it adds latency if we're looking for different kinds of information. So now in this particular environment in the database, let's say 80% is going to hit the cache. So half of the traffic is read, half the traffic is write. But guess what? 80% of the traffic comes in like this. Someone asks a question from the database. The first time it hits the cache, the second time the query and the information was stored in the cache. Now user 2, 3, 4, 5, and 500, all the way to 500, all want the same information, and that information hits the cache, and the cache responds. So now that the database is doing basically only 20% of the read loads because the cache is doing 80, now, for example, the read load goes down to, say, 20%. And that means now we have 80% left over for writing. So this can also enhance the performance. It can enhance reduce the latency when we go to, say, a web server that has to reach and retrieve information from a database. It can do that very well. But if the information is different, it would also cause a problem. Now, the next example I'm going to give you is I want to show you a content delivery network. Because these are all types of caching, and I'll show you a reverse proxy too. Let me show you a reverse proxy, and then I'll show you the content delivery network. I think that'll be easier to understand. In this example, we have a reverse proxy, and guess what? It's going to look and feel a lot like a load balancer. So this is a reverse proxy, and what a reverse proxy is it's basically a load balancer with caching. So we may have an environment where, let's say, we have a whole bunch of web servers. And these could be, for example, for internal web servers, because you may not want to be putting you most likely won't be wanting to put your private servers on the internet using a content delivery network or anything like that. So you might need another way to do this for intranet servers, not internet servers, things that are internet facing. But in this particular case, what we have is a reverse proxy cache. And here's how this works. Just like a load balancer, let me move these down so I can illustrate this a little better. The traffic is shared amongst all the web servers. So maybe this session is sent to this web server, or this session is sent to this web server, or this session is sent to this web server, or this session, or however they want to load balance it. So we still get load balancing just like we would out of a load balancer, but also now we have caching. So where does this typically come in? So let's say we have a user. And in this case, the user wants to go to the web server. So now the user goes to the web server. They request the home page, for example. Now that user goes to the load balancer, it's not cached, it's a cache miss, it gets responded to by the web server. And the web server responds. The reverse proxy / cache stores the information and it sends it to the user. Now that was user 1, but now we've got user 25. And user 25, as well as 22, 23, 22, and 21, all request the same home page. So user 25 hits the reverse proxy has it hits the cache, and it actually responds to user 25. Now we've got let's say user 38, and user 38 now requests something different. So now user 38 requested something different. It goes to the reverse proxy. There's not cache there, cache miss. Now it goes to the second web server, for example. Second web server responds, and then it gets sent back to user 38. And this goes on and goes on and goes on. So this, again, can reduce the load on the web servers. We need less of them, and we'll get reduced latency because the cache is DRAM. And the web servers are going to be using potentially block storage, which is a lot slower than DRAM. So this is a reverse proxy setup. All right, we're going to do one more. We're going to create a content delivery network too right now. So now in a content delivery network, we have our web servers. And of course, we have all of our security stuff in front of it, but we're not. And we're just talking about CDNs here, so I don't want to get too complicated. So we've got our web servers. They connect to the security stuff. The security stuff now connects to a CDN. Which has caching servers all over the world in internet peering points. So now that we have the CDN, let's say we've got 3 places. So we've got Santorini, beautiful place if you haven't been there. Let's say in addition to Santorini, we have Athens. And we have Crete. Let's assume that we actually have internet peering points in all these places for a little while. So in this particular environment, let's see how the way this would work. And let's assume the CDN is all different geographic people for Santorini, Athens, and Crete. So in this case, we have our first user, and our first user is Aguilo. And Aguilo wants to see that web server. He's in Santorini, so Aguilo sends a request, and it hits the local point of presence in Santorini, now where the content delivery network is, but it's not stored that yet. So now the message goes to the content delivery network, and then it sends it all the way back to the web server. And when the web server responds, and then it gets stored on the CDN. So now we've got another user in Santorini, but this user is Apostoli. We can keep the A this way. Now, Apostoli decides that he's going to go to Santorini. He also is in Santorini. He hits the local Santorini CDN, and the local Santorini CDN already has it. So now Apostoli gets it very quickly. Now, for as long as possible, people request that same web page. Maybe the cache times out in 24 hours, or what do you set it? Or you set it to? The cache for all the people on Santorini is going to respond immediately. And what if this website was hosted in New York City? The cache would be storing it in Santorini after it was requested, which means we wouldn't have all the global networking latency time. So it's going to reduce the latency over here, give a better experience to the users, reduce the workload here. Plus, most content delivery network providers have really good DDoS protection services, where they block bad HTTP requests and things that look like DDoS type attacks. Now, just because the user in Santorini was able to get things through the cache, now we have a user in Athens. So now in this particular case in Athens, we have Vigeli, and Vigeli decides that he wants to go to see the same website. So Vigeli's close. He hits the Athens point of presence. It's not cached in that point of presence, so it hits the CDN. Now, maybe in this case, there's a regional CDN that's headquartered in the Mediterranean that automatically responds on behalf of this, depending upon how the caching environment's set up. But let's in this case say it's not. So we had Ovigelis who decided he was going to get the same web page, and he went to Athens, and that got sent to the content delivery network, and because there was a cache miss, and then it now hit the web server. Now the web server again is going to respond over here, and it'll be cached in the CDN. And now that Vigeli's done, it's okay, because when Maria decides she wants to see the website, and Maria is inside of Athens, the Athens CDN will respond, and she's going to be really happy because she got very low latency access. And this is another type of caching called the content delivery network. So there's lots of caching we use, and now you know what. So now let's talk a little bit about the kind of caches we'll be dealing with in Google Cloud and otherwise. Caches typically use DRAM. And here's the reason. We can think of hard drives being slow and DRAM being super fast. Now we're getting to a point where NVMe drives in RAID are getting really fast, but the latencies and the speed of DRAM is fast. So what we're dealing with is we're going to deal with servers that have a huge amounts of DRAM, and we're going to be storing this frequently accessed information in DRAM. So if it's already there, it's not going to have to hit the hard drive. The hard drive's not going to respond. And if it's block storage, which is even going to be slower, which is accessed over a network, and there's going to be latency. So the cache is going to do a lot to reduce the load on these servers and potentially increase the performance if it's all for similar information. Now, we've got applications that need high throughput and low latency. Caching can really help here. So maybe we've got some web applications where we want to reduce performance. Reducing latency might even help them rank higher in search optimization, for example. We might want to do real-time analytics. We have to analyze a lot of information fast. We might want to create a leaderboard or leaderboard data for a gaming platform. All this kind of stuff really benefits well from a cache. And GCP has a cache that they manage for you, and it's called MemStore. And it's managed in-memory caching services for Redis. And Redis is a very popular choice among caches. And they also have memcached, which is a simple key value store for caching objects. Now, I'm going to make it very clear. You can use this Google's memory store to do it, or you could create a virtual machine with lots of DRAM and install Redis yourself if you wanted to, just like you could in the data center. But this is the GCP managed equivalent of that. I just want you to know you have both options. So obviously I described a little bit about how content delivery networks are used for caching for web applications and pushing content closer to the users. And I also showed you application level caches, for example, that could be used to reduce repetitive paths, say, going into a database. Now let's talk about the kind of patterns and use we have with regards to caching. We have something called read-through caching. And then we have something called write-through caching. And this will affect the way the information is pulled or stored. With read-through caching, the data is fetched from the cache first. If it's not present in the cache, it goes back to the database or the source, just like I showed you. That's read-through caching. Meaning, we go to the cache. If it's not there, we go to the source and we pull it. And this way we make sure the cache always has the most requested data. And why do we know it's the most requested data? Because it's what the users are requesting. So this is one of the good things about read-through caching. Now let's talk about write-through caching. Now here, we put the data in the cache and the storage at the same time. So if you think about this, what are we really talking about? We're actually doing two different things. So we're taking our data and we're putting it in storage. Whatever that is, it could be where we could be storing information. It could be storing it into a database, but let's just call it storage. But in this case, we're writing it to the storage and the cache at the actual same time. So the data is in both places simultaneously. Now, if we deal with this, if you think about it, if the data is written to both at the same time, that's going to guarantee that the cache and the database are going to have the same information. Now, if you've got an application that needs a strict data consistency, meaning where you don't want to go to the cache and potentially pull information that's a little older, you want the freshest information at all times. This is going to give you that guarantee. So sometimes you need that. So that's going to be right through caching. Now, I want to talk about write back caching next because, all these caching types that we have, they're similar, but they're different, and I want you to truly understand them. Now we have write back caching. And here we have something that's slightly different. Here we have the data is first put to the cache. And the data is first written into the cache, and then after it's written to the cache, then the data is written to the database. So first here, and then synchronously copied to the database. Now, if you think about this improves the performance for write-heavy workloads because it sticks it to the cache, which has the space, and then moves it to the database when the database can handle it. But I want you to think about this. This is DRAM, the cache. So if the cache were to crash, for example, or something happened to that server, or the server was powered down or crashed and rebooted or whatever, we're going to lose data that should have been in the database. So if we need the most speed, write back caching gets us here, but it also risks data loss. So if we need speed and the risk of data loss is acceptable, then we use write back caching. I hope you're starting to see that each one of these options does something well and something not so well. That you gain something with one option, architectural option, and you lose something with another architectural option. So when we're dealing with cloud architecture, enterprise architecture, security architecture, AI architecture, it's not about picking the best tech. It's really about looking at the challenge we have and then looking what kinds of technologies, for example, will best meet that challenge after examining all the trade-offs to meet that. And these are organization-specific challenges, not any just generic, everybody gets the same thing kind of challenge. So let's talk about that memstore option. You've got as Redis and memcached, same as AWS and would offer and others. Now, Redis is used for when you need advanced data structures. Things like sorted sets, geospatial indexes. It's got a lot of capabilities. Whereas memcached is simple, it's well suited for object caching. Memstore handles scaling, patching, replication automatically, and it provides high availability, low latency performance. Why? It's managed for you, but it's also you lose control. That's the thing to remember. They manage everything for you. Now, memstore integrates seamlessly with other GCP services, making it an easy choice for people that are using it because it's simple, it's elegant, and it's managed for them. Now, Google has a content delivery network, and the Google Cloud's content delivery network accelerates the delivery of web content by caching it at the edge. And these are edge locations around the world, typically speaking. These are what's called internet provider points of presence. So this is typically where this is at. And I'll show you the way this would look like from an architectural environment so you can understand what these point of presence and caching servers actually are. So what will happen is we're going to have these points of presence. And the way this works, let me just knock out the filling here, is we have companies that'll have high-speed connections coming into the building, wide area network. So I'm going to just label these as WAN. And this is going to be coming from all kinds of ISP. And these can often be some pretty big, expensive private lines. So let's say this is AT&T that's coming in. And let's say this is Verizon. Let's say this is Telefonica from Spain. Oops, I think I'm going to have to make this one a little bigger. Telefonica. So let's say this one is NTT coming in, Nippon Telecom from Japan. Let's say this is Etisalat in UAE. And they're all coming into the same building. Now, by doing this, for all of these folks to be connected, all they really need to do is plug into a switch or plug into various routers. And what'll happen is they'll do BGP peering with them. So they'll have connectivity, they'll exchange routes via BGP, and routing will be set up. Now, so here's what's going to ultimately happen for things to understand. So if you've got a customer of AT&T's, actually, let me draw internet routing real quick, and then we're going to come back to this. So here's the way internet routing works. So let's say you have AT&T over here, and you have Verizon over here. And you have NTT over here. We've got there's a reason an NTT. So NTT's in Japan. These two are in America. So what happens is these have links between them. And here's the way the routing is. So let's say we've got a user in Japan, and the user in Japan wants to access a website that's hosted by AT&T. Now let's assume that NTT has a connection to Verizon. So what'll happen is NTT will go over their wide area network or whatever it is, send all the data to Verizon. And then Verizon has to send it all the way back to AT&T, and then this can be sent to the website. The website will respond, and it'll go through AT&T, through Verizon, through NTT. Now, wide area networking links like these can be incredibly expensive. And once they get full, the company needs more of them or bigger ones. So these can be huge, and these are hugely expensive. So now let's look about why internet service providers love content delivery networks and why these things are so great for performance. So let's say we've got a caching server here. Now the request comes in. Let me just, oops. Let's assume the caching server now has access to all these local internet service providers somehow because they're already in the same building. All right, so let's not do that for right now. Let's keep this exact and simple. So now you've got a user request, and the user was on NTT. Now remember, they had to go from NTT. Without these caching type environments and server environments, they would go from NTT, assuming we didn't have this point of presence, over the wide area network to Verizon, over the wide area network to NTT. But now we're all in the same building. So now the request comes in from NTT. The request from NTT ultimately hits the caching server, and it hits AT&T and the caching server in the same building, and it responds. So now we kept all the internet traffic all directly in the same building. and we didn't have to burn up that wide area network that the providers had coming into this building. So this dramatically decreases latency because we wouldn't have to go from Japan all the way to, say, the America, somewhere where Verizon was, all the way to another internet service provider in America like AT&T. So this is why we have our points of presence, and this is where these CDN or caching servers typically live. Now Google has their own CDN that they have made up. And, they've got a little bit of experience being reachable at fairly low latency all across the world. Google's used pretty much all across the world. YouTube's used pretty much across the world. So Google's pretty good at making this. And it obviously integrates very seamlessly into other Google services. And the thing to remember is, do you use the cloud provider's content delivery network, or do you use somebody else's, like Akamai, for example? Or do you use several content delivery networks? Because if you only have a single content delivery network, you're basically introducing more single points of failure into your architecture. So you'll have to think about that in your architecture and evaluate all trade-offs to figure out what's best for your client. So Google CDN supports obviously caching, but it supports static and dynamic content. Static content is the stuff that's always the same. Dynamic content is things that change more frequently. Obviously, it reduces latency for users in most cases, and it can cache images, CSS, or even JavaScript. Let's talk about some security in caching. So when we're dealing with memstore, remember, in a cache, we're going to have a lot of information incoming in and out of the cache, and we want to protect that. So memstore encrypts all data in transit. So anytime your data is moving between the application and the cache, it's going to be encrypted. It integrates with the VPC to make sure that traffic will remain isolated from the public networks. And GCP's identity and access management will allow you to be fairly granular in the permissions for accessing, say, caching resources. And that way we can ensure that only authorized users and applications can interact with cache. Okay, well, we are back to see if anybody brought in any questions related to the content we brought. And while we wait to see if any questions pop up, Leo, do you want to talk about the next labs you have coming up and what's going to be on them?
Sure. The next labs are about how to create a persistent disk, how to attach that disk to a virtual machine. In another demonstration, I will show how to create an object storage bucket, or cloud storage as Google calls it. And the third lab we will have today is about hosting a static website in a cloud storage bucket.
Sounds great, Leo. Sounds like a whole lot of fun. So just in case any questions are here, I want to remind everyone that we've got a study guide to assist you with Google Professional Cloud Architect exam. My team will drop it in the chat box, but it'll also be in the description of this video. I want to remind you that tomorrow at 11 a.m. We'll be online to answer any tech career questions you may have about your career. We'll do that at 11 a.m. On Wednesday. We normally be doing it in the later afternoon, but we'll do it at 11 a.m. tomorrow because of the boot camp time. On Thursday, we have a How to Become an Architect webinar where we'll go over the architect role. We'll talk about what we do. We'll talk about why most people aren't getting hired and what they could easily do to get hired by shifting and changing around a few things. And then we'll answer any questions you have. And of course, they'll all be free. And I didn't see any questions that popped up. So give me a hashtag, Google Professional Cloud Architect. And let's get into Leo's labs.
Hello. In this lab, I will demonstrate how to create a persistent disk and how to attach a persistent disk to a virtual machine. I will start on this page, cloud.google.com. Here you can perform your login if you are not logged into your Gmail account yet. You can open Google Cloud Platform console, and you can also access Google documentation by clicking on Docs. Here is Google Cloud documentation. and we recommend you read the documentation about the services you want to use. You can explore this documentation on your own. For this lab, I will click from the left side menu, I will click Compute, then Virtual Machines, and then Compute Engine. Here you have the Compute Engine documentation with a lot of information, some training opportunities, some related videos. All this for you to learn more about the Compute Engine. Here from the Guide section, I will click Create and Start a Virtual Machine. This will open the page with the details about creating and starting virtual machines, the steps you need to take or execute, even before starting to execute these steps to create a virtual machine. Here are some methods to create and start an instance. And there is a lot of guides here on the bottom how to create different virtual machines for different purposes. From the left side menu, I will scroll down till I find Manage Storage. And from Manage Storage, I will click Disk Types, and then I will click About Persistent Disk. Here is the documentation about persistent disks, the different types of persistent disks, and remember, the different settings are a result of the business needs, of the use case needs. You choose what is the best solution to solve one specific problem. Here are some links about zonal and regional persistent disks. This is about redundancy. Zonal means you have one persistent disk in one availability zone. A regional persistent disk, once you create a disk, Google will replicate this disk in different availability zones inside one region. And of course, different redundancies have different costs from the perspective of the public cloud provider charging you for the services you use. There are other informations like durability, the machine series and their supports for the different types of persistent disks, about capacity, again about zonal persistent disk and regional persistent disks. There are some pictures here for you to learn more about those differences, interface types, encryption to secure the data, and some restrictions. And all the way to the bottom, we find the What's Next session. And here, the first link is learn how to add a persistent disk volume to your virtual machine. I will click this link to open the documentation. And here is the page, create a new persistent disk volume. It presents some steps. You need to make sure you have done them before you start creating or trying to create the persistent disk. This is about authentication, and to use the console to create the persistent disk doesn't require any authentication after you have already performed your login. Here is the session about adding a non-boot disk to your virtual machine. When you create a virtual machine, you will need to create a boot disk for that virtual machine as well. The boot disk contains the operating system to boot that virtual machine, and also is where you install the applications that you run on that virtual machine. A persistent disk is a secondary disk that in most cases is used to store data that you want to make independent of the virtual machine. So from this section, we will follow the steps to create a persistent disk and attach it to a virtual machine. The first step is to go to virtual machine instances page. Right now, I don't have that page open, so I will right-click the console link here and choose to open in a new tab and switch to that tab. From the left side menu, I will select Compute Engine and then VM Instances. Going back to the documentation to see what the second step is. The second step is click the name of the virtual machine where you want to add a disk. And the step 3 is on the details page, click Edit. Let's click the name of the virtual machine. And here we are in the details page. You can check the settings of your virtual machine and you can scroll down to check that you have the boot disk, but there is no additional disks attached to this virtual machine. You can click Edit and then scroll down. Here there is some information about the boot disk and the deletion rule regarding the boot disk. You can choose to keep the disk when the virtual machine is deleted, but the most common setting for this is to delete the disk with the virtual machine. The setting or what you choose will depend on the needs you have for the virtual machine. I will keep scrolling down and find the additional disks option, because the step number 4 is to click Add New Disk under Additional Disks. I will click Add New Disk. I will accept most defaults here. The name is fine for me. The location of the persistent disk, again, is between single zone and regional disk. It's about redundancy. If you want to learn more, click the Learn More link. I will accept the source, the disk source type, the disk type as well, the size. I will scroll down to find the deletion rule for this disk. As this is the secondary disk, a persistent disk, I don't want this disk to be deleted if the virtual machine is deleted. If the virtual machine gets corrupted, I can detach this disk from the virtual machine and attach to another virtual machine. So I want to keep this disk even if the virtual machine is deleted. So making sure the keep disk is selected, I will click Save to save these configurations. And here it shows new disk, this one, blank, balanced persistent disk with 100 gigabytes in size. You can click Save to save this disk. And if I go back to the documentation, after clicking Save, there is an information, a very important information here. After you create the new disk and attach it to a virtual machine, you must format and mount the disk so that the operating system can use the available storage space. This means up to this point, the operating system doesn't know about the persistent disk we have just created. To allow the operating system to use the disk, I will go under the What's Next section and then click the link to learn how to format and mount your new disk to a Linux virtual machine. Here again, if you attached a new blank disk to your virtual machine, before you can use it, you must format and mount the disk. If you attached a disk that already contains data, then you must mount the disk before you can use it. So the steps to format and mount the disk, first I need to connect to the virtual machine. So going back to the VM instances page and clicking the SSH button to connect to the virtual machine. I will click back here. Here I have the virtual machine, and here I have the SSH button. There are different options to connect to the virtual machine, and you can even use another SSH client if you prefer. But for this lab, I will use the cloud native SSH client provided by Google. I will click here on SSH, bring this new window here. Authorize the SSH in browser. And here is the prompt from inside the virtual machine. I can check the disks attached to the virtual machine and attached and mounted to the virtual machine. And here we have the boot and some system firmware, different directories or different mounting points for some partitions we have on the boot disk, on the main disk created with the virtual machine. Now, after we format and mount the persistent disk, it will appear here on this list. Going back to the documentation, now going to the format a non-boot disk on a Linux virtual machine is exactly the type of disk we are going to format, because it is a secondary disk, not the boot disk. The first step is to use the terminal and use the symlink created for your attached disk to determine which device to format. I will copy this command, bring the SSH window here, right click, paste the command, and hit enter to execute. So here we have the Google-disk1 disk that was created, and its symlink is SVB. From the documentation, the next step is to format the disk using the make file system tool. Warning, this command deletes all data from the specified disk, so make sure that you specify the disk device correctly. Let's take a look at the command we will execute. So it uses the make file system tool, and it has a red field here, file system type, and we have replace the following. Replace the file system type with the file system type, for instance, ext2, 3, 4, or XFS. Here we have a comment or a recommendation. You can use any file format that you need, but this means Google recommends a single ext4 file system without a partition table. So we will replace file system type with ext4. In the same command, we also have the specification of the device where the file system will be created. So there is device name here on red, and the information is device name, the device name of the disk that you are formatting. For example, using the example output from the first step, you would use SDB for device name. from the command we executed, we know the symlink for this device is actually STB. So we will replace file system type with ext4 and replace device name with STB. I will copy the command, bring the SSH window. Let's see, copy the command, bring the SSH window, paste the command here, and replace device name with STB, and replace file system type with ext4. And then I can press enter. After creating the file system or formatting the disk, the next step is to mount the disk. To mount the disk, we need to create a directory that serves as the mount point for the new disk on the virtual machine. You can use any directory. The following example creates a directory under mount/disks. So in this command, I will replace the mount_dir red text with the name of a directory I want to create. I will copy the command, bring the SSH window, paste the command here, and remove mount_dir, and enter, let's call it persistent data. This will create a directory named persistent data where the STB device will be mounted. So all the content of the STB disk will appear inside the persistent data directory. If we list the content of the mount/disks directory, we see the persistent data is there. We also have another folder there that is not part of this demonstration. We will use persistent data as our mount point. After creating the directory, we can use the mount tool to mount the disk to the instance and enable the discard option. The discard option is already here in the command. I will need to replace device name with SDB and mount_dir with persistent data. I will copy the command, bring the SSH window back, paste the commands here in the command line, and do the needed replacement. Persistent data. Double check your typing to avoid any mistakes. And here I will replace the device name with STB. I can press enter now. And if I issue the df-h command again, I will see that now the device STB is mounted to the directory mount/disks/persistent data. We can list the content of the mount disks persistent data, but it is empty because we just created the directory and we just formatted the disk. So the disk at this moment contains no information. After mounting the disk, the next step is to configure read and write permissions on the disk. Here again, the mount_dir is the name of the directory we created for mounting the disk. I will paste the command here and replace mount_dir with persistent data and hit enter. Up to this point, we have created the disk, we have formatted the disk, attached or mounted the disk to the persistent data directory. The disk is working. If you want to save data to that disk, you can already use that disk as a database location to save data or as a persistent data storage. But if for any reason the virtual machine restarts, that persistent disk will not be mounted automatically. To correct that, we need to configure automatic mounting on VM start. The first step to do this is to create a backup of the current etc fstab file. I will copy the command, bring the window back, paste the command, and hit enter. If we list the contents of the etc directory and we limit it to fs, to any file that starts with fs, we will list the fstab and the fstab.backup, which is the backup we just created. And why do we need to create backup? Because this is a sensitive file for the operating system and we need to avoid any mistakes. So we have the backup just in case when editing the current fstab we make any mistakes, we can recover it from the backup. The next step is to use the blkid command to list the UUID for the disk that we just mounted. We will need this information to add into the fstab file. I copied the command, I will paste it here, and I will replace device name with SDB, and here is the UUID. I will copy this to another tool here, a text editor. This will not be visible for you. I just need to save the information because we will need to replace this field in the next step with the UUID value. We also will need to replace maltir with the name of the directory, persistent data. We will need to replace file system type with ext4, and we will also need to replace mount option with a new information that we haven't seen yet, but here it is. Mount option specifies what the operating system does if it cannot mount the zonal persistent disk at boot time. There is some information about the documentation here. I will skip to the last statement to let the system boot. Even if the disk is unavailable, use the no-fail mount option. So I will replace the mount option with no fail to allow the virtual machine to boot even if this disk is not available for it to use. So I will copy this command and I will open the etcfs tab in a text editor to add this line and replace the needed fields. I will bring the SSH window, and here I will remove this data from here. I will issue with escalated privileges. This is required because the fstab is a system file and a regular user cannot edit a system file. So I need to use sudo to act as the administrator of the system and have privileges to save the file after I edit it. Sudo nano etc fstab. Here is the current content of the fstab file. I will move the mouse using the arrows on the keyboard. I will move the mouse to the point I want to paste the information I have on the clipboard. I right click and then select paste. And now I need to replace the red tags or add texts from the documentation. Mount option is no fail. The virtual machine will boot even if the persistent disk is not available. The file system type is ext4, and the mount div is persistent data. Double check to make sure the name of the directory is correct. And the last information I need to replace is the UUID value. I will copy this value from the place I saved it, and I will position the cursor here, right click, paste. So now I have the line with all the information inside the fstab file. To save the file, I will issue the Ctrl+X command to exit, but before exiting, the editor itself will ask me if I want to save the file. So hitting Ctrl+X on my keyboard, it asks save modifier buffer. I will answer yes by hitting the Y key, and now it asks if the file name to write is etc fstab. I will just hit enter to confirm that this is the name of the file I want to save. The next step on the documentation is exactly to use the cat command to verify that the data stored or saved there is correct. I will copy the command here, bring the command line interface back, right click, paste the command, and then hit enter. And here we see the UUID, the mount directory, the file system type, and the mount option. So all information is correct. This means that the disk is ready to be used. If the virtual machine restarts, the boot will automatically be mounted to the virtual machine. So we will go here on the disks tab. We see the disk, the VM01, that is the boot disk, and the disk 1, that is the persistent disk. And we go back here to the VM instances page. I will issue a command. I will open here on the three dots, more actions, and I will stop the virtual machine. By manually stopping the virtual machine, I will simulate a restart, automatic restart when in production, for example. And once I hit stop, this message appears asking if I want to stop the VM01, and it informs that you will be billed only for these preserved resources, the persistent disks and static IP addresses. The virtual machine will shut down. If processes are still running, the virtual machine will be forced to stop and files may get corrupted. For this lab, I will just hit stop, even because I don't have any applications running on this virtual machine. I will hit refresh to verify if the virtual machine is already stopped. After some time, the virtual machine is stopped. I'll go back to the disks tab to show that the operating system, any applications that were installed on that boot disk, they are still there, ready to be restarted. Nothing is deleted by stopping the virtual machine except data on memory. If you had applications running with data in memory, you will lose this data in memory, but once you restart the virtual machine, it will start new as your virtual machine with the applications installed, ready to be used again. The same way, the disk one, the persistent disk, will still be there, and all data saved on this disk will be still there on the disk when the virtual machine boots up again. The idea of stopping the virtual machine was to check if the persistent disk will be automatically mounted once the virtual machine starts again. I will go to the three dots again and issue, well, is the virtual machine running or stopped? The virtual machine is stopped. I will go to the three dots and then start or resume the virtual machine again. Start the virtual machine, yes. I'll hit refresh to verify when the virtual machine is ready and working. Now the virtual machine is working. I will hit the SSH key again to open the SSH window. And I will authorize and I will issue the df-h command to verify if the persistent data is mounted with the STB divide, and it is. So the persistent disk is automatically mounted after a virtual machine restarts. I will exit the SSH window and I will now delete this virtual machine. I need to select or check this box to these options to appear, and I will click delete. And again, it will ask for confirmation. I will click delete again. And I'll click refresh to verify when the virtual machine is deleted. And I will check what happened to the persistent disk. The boot disk was configured to be deleted with the virtual machine, but when creating the persistent disk, I selected the setting to keep the persistent disk even if the virtual machine was deleted. I will hit refresh again. Now I will hit refresh again and it doesn't show the virtual machine anymore and it says instance deleted. Now let's go to the disks tab. And as expected, the disk one, the persistent disk with 100 gigabytes in size is still here. This means you can attach this disk to another virtual machine and use the data that persisted on this disk after the virtual machine was deleted. By selecting or checking this box or clicking the three dots here, you have different options you can execute with this disk. You can create instance, you can create snapshot, create an image, clone the disk, create secondary disk, and you can also delete this disk. For this demonstration, I don't have any use for this disk. I will hit delete just to demonstrate how you can delete all the services you used during this LED demonstration, so you stop being charged by Google or you stop being charged on credits you have with Google. I will hit refresh. And now there is no disk in this tab. In this lab, I demonstrated how to create a persistent disk, how to format the disk, how to attach the disk to a virtual machine, and at the end, how to clean up and delete all the services used in this demonstration. Thank you for watching and see you in the next lab.
Okay, that was fun, Leo. Really enjoyed watching that. So we are here back to see if anybody has any questions. Please ask questions. Leo, did you want to say anything about the last lab before I ask you about the new labs?
You mean about this one we just saw, or the next one that we will play?
First, the last one, and then the next one.
Okay. These demonstrations, everybody needs to understand, they don't cover all aspects of using the services. They don't cover the security, they don't cover the costs, they don't cover many aspects of the services, because the intention is to demonstrate how to use the service in the Google Cloud platform. To know and to be aware of all aspects, please refer to Google's documentation.
That's a really great point. When you think of everything, it's going to take a whole cohesive strategy, but we're trying to show individual components here. So that sounds great. Leo, what's going to be in your next lab?
The next lab is about creating a bucket in Google Cloud Storage, in the Google's object storage named Cloud Storage.
Sounds great. Yeah, these marketing providers, S3, Blob, Cloud Storage, all the same tech. Who thinks of these names? But sounds pretty good. As a reminder, if you just got here, I see one person just did. We've got the previous 6 days. This is day 7 on our Google Professional Cloud Architect Bootcamp. My team will drop a link to the playlist in case you just joined us. You can go catch up on it. Please remember, we've got a corresponding guide to help you with this Google Professional Cloud Architect exam. It's about 550 pages. My team created it for you, so it's free. Go use it to help pass that Google Professional Cloud Architect exam. And that way you'll be a Google Professional Cloud Architect certified. So that is there, and it is free. Tomorrow, I will be here at 11 a.m. to answer any cloud career questions about anything. Security architect, cloud architect, AI architect, it doesn't matter. I've been in tech for years, advised almost everybody in various tech roles, and I want to do what I can to help you. So that'll be free. And then on Thursday, we're going to have a How to Become an Architect webinar where we'll talk about everything you need to become an architect, and that is free too, like a cloud architect or an enterprise architect, and we'll meet and talk on Zoom. So Chris from my team drop that link in. Well, give me a hashtag Google Professional Cloud Architect. There's some things so they know you're here. Or talk about Leo and his cool labs. I'm fine with that too. But I just want to know you're here. Let us know in the chat box. And then Chris, let's roll with Leo's next lab.
Hello. In this lab, I will demonstrate how to create a Google Cloud Storage bucket. I will start by opening a new tab and visiting cloud.google.com. This is the same page where you can log in using your Gmail address and you can access Google's Cloud Console. But right now, I will click the Docs tab here to open Google's documentation. And then here on the left side, I will scroll down to find storage. And then after clicking storage, I will click Storage Solutions and then Cloud Storage. Here you can see the documentation about cloud storage, some training offers. I will go back up here and click Read Product Documentation. Here is the product overview about cloud storage. Cloud storage is Google's name for the object storage type of storage. You can cover this content on your own, understand Google's hierarchy, the tools you can use to create and manage and manipulate cloud storage buckets, the options for securing your data. And here under Quick Start Guides, we have the option for the Google Cloud Console Quick Start. I will click this option. I will scroll down. Here are some steps that you probably have done already, creating your Google Cloud account, making sure that billing is enabled. If not, follow those steps. If you have already done them, you should go to the Create a Bucket section. Here, the first step is to go to Google Console and then to the Google Cloud Storage Buckets page. I will change here for the console and then open the left side menu, Cloud Storage, Overview Buckets. Here we have a blank page on Google Buckets, and we have the option to create a Google Bucket. Here on the right, you will always find documentation about the topic you are visiting here. I will click Create to create a Google Cloud Storage bucket. Give the bucket a name. Let's see. There are different options here. I will not cover all of them, but I will only show the simplest way to create the bucket with using standard or default configurations that Google already provides for you. You should open all the sections here to learn about the different options when creating your bucket. Click Continue to move to the next section. Here you can choose the redundancy for the data you want to store on a bucket. You can choose multi-region, dual region. I will just select the region option for simplicity and select the region, the Google's region I'm closest to. In my case, I'm located in São Paulo. I will choose this region. You should choose the one that is closest to you. I will click Continue to move to the next section. Here, choose a storage class for your data. On the bootcamp content, you probably learned about the different classes for the data. The data that is frequently accessed should be stored in one class. Data that you want to store for a longer period can go to another class of data, and the prices vary according to the class you choose. I will accept the standard class and click Continue. Choose how to control access to objects. Here, Google by default selects Enforce Public Access Prevention on this bucket. You are enabling the prevention. You are stopping public access to this bucket. Later, we will see how you can allow public access to your data stored in buckets. I will just accept the defaults here and click Continue. Choose how to protect object data. Here you can protect from soft delete, meaning you keep copies of deleted data for some time to make sure you really wanted to delete that data. And you can use default retention or set a custom retention period for the soft deletes. And you probably learned about object versioning as well and retention on the bootcamp content. I will just click Create to create the bucket with the mostly default settings. Here is a warning that public access will be prevented. and I will just click confirm to create the bucket with this configuration. Let's go back to the documentation, and after creating the bucket, the next steps are to upload an object into the bucket. I will follow the instructions and right-click this picture, select to save to one of my directories here. The next step is to go into the cloud storage bucket page and select to upload the picture to the bucket. You have the option to create folders to organize your data, but here I will just click upload, select upload files, find the picture I just downloaded and click open. It shows that one file was successfully uploaded, and here is the picture in my bucket. If you click the picture or object name, you will see it has an authenticated URL. Let's copy this URL, open a new tab, and paste the URL here. And here we see the object or the picture in this case. This was only possible because I am getting the authenticated URL. Remember, this bucket is set for not public access or permissions. And here we can see there is no public URL for this object or for this bucket. Let's close that picture and go back to the documentation. Now that I have an object in my bucket, let's see how I can download that object. If you are inside the bucket, you have the object listed here on the left. You can click the three dots and you have download, or you can click this down arrow here to download the object on the same line. If you have more objects, you have those icons for each object. The next step on the tutorial is to share the object. To allow public access to the bucket and create a public accessible URL for the image, the first step is to click the Permissions tab above the list of files. Let's go there and find the Permissions tab. So here inside the object, you have the Permissions tab. If you are in the list of buckets, you need first to click the name of the bucket you want to modify, and then you can find the Permissions tab. And the documentation instructs to grant access, to click the Grant Access button to add a new principal, and then add principal and enter all users for this new principal. So let's go back there. Grant access. Here I enter all users and select the role. Well, before I can select the role, adding all users makes this resource public and accessible to anyone on the internet. Principals, all users, and all authenticated users cannot be added since public access prevention is enforced on this bucket. So we will need to remove the public access prevention first and then add the principals and the role. Well, in this page, I already have the public access note here, and then the option to remove public access prevention. It shows a warning that this will become accessible, and I click confirm to remove the restriction and to make this bucket public. Now I can click grant access and enter all users as a new principal, and then select the role as cloud storage bucket viewer. Each role will allow the user to perform different actions on the bucket and the objects inside the bucket. For this lab, we will use the storage bucket viewer as instructed. Now I can click save and confirm the question, are you sure you want to make this resource public? I click allow public access. Now let's go back to the objects tab. And here is a warning that this bucket is publicly accessible because all users or all authenticated users have one or more permissions. Remove these principals to stop public access. At this point, I will click the name of the object here. Now it has a public URL. I can copy and paste in a tab, or if I'm sending an object, a video, any file to another person, I can send this link to the person. This error message only appeared because I selected the wrong role in the previous step. If you selected the storage object viewer, you should see the picture and not this error message. If you go back to the bucket and you open the three dots for this object, you see the different actions you can apply or execute on this specific object inside the bucket. You can copy the authenticated URL. If you are using the command line tool provided by Google, you can copy this other URL, edit metadata for this file, edit access. You can copy, you can move, you can rename the object, and you can export to Cloud PubSub, or you can scan with sensitive data protection. So you have different actions you can execute on this object. Now, to remove the public access, we go again to the permissions. And here at the bottom, we have the principals and their roles. So I will click all users, and then I click remove access. And I need to confirm I want to remove access. I want to remove all users from the principals list. To completely prevent access or to prevent public access to this bucket, you also need to click here on prevent public access and then confirm you want to prevent public access to this bucket. And now if I try to access that object again, now the object has no public URL because we just removed the all users principal. Going back to the bucket, we can create folders to organize the data inside the bucket. Here I click create folder, and then I give the folder a name, and click Create Folder. And I can create another folder, let's say for soundtracks, for instance. And then now I can select the three dots for the object I want to move, select Move. And then I select the Pictures folder and click Select to move. And then I click Move to finally move the picture inside the Pictures folder. Once you are done with the objects, or if you have already used the object and you want to remove them, you need to click the checkbox, and then from the options that appear, you can click Delete. And there is a soft delete policy enabled, and the message needs to confirm you want to delete this object. You can confirm by pressing Delete. Now, let's say you are done with your bucket and you want to delete the bucket completely. You can select the checkbox here, and then the delete option will appear. You click Delete, and again, you need to confirm the deletion by typing Delete and then pressing the Delete button. You are back to the buckets page, and this is empty because there is no bucket inside it. That's it for this lab. I demonstrated how to create a bucket using Google Cloud Storage Service, how to upload a picture or an object to the bucket, how to change the permissions to make it accessible from the internet, and how to delete the object and the bucket. See you in the next lab.
Okay, welcome back. That was the second lab for the day. Leo is going to have one more for us. Were there any questions that popped up? Because if there are any questions that popped up, we want to answer them because we want you to leave this session fully prepared and fully comfortable for that Google Professional Cloud Architect exam. So give you a few seconds to see if any of these questions come in. While we do, Leo, do you want to talk about what's in the next lab?
Sure, Mike. The next one will leverage an object storage bucket to demonstrate how one can host a static website. Of course, the demonstration is not a complete website, but is a minimum infrastructure needed to host a static website in a cloud storage bucket.
Well, that makes sense. Obviously, you're not going to take up as a career as a web developer, given your experience in cloud engineering and cloud architecture. But I completely appreciate it. Web developers make great websites, but that's what they do. So thank you for making that clear for others, that there's a large number of people in tech. We'll have web developers, we'll have application developers, we'll have application architects, we'll have AI engineers, we'll have AI architects, we'll have data scientists, we'll have cloud engineers, DevOps engineers, we'll have network engineers, we'll have network security engineers. It's going to take a big team. And part of that is be able to lead that team and get the right team to get the result outcome. So that sounds good. So give me a hashtag Google Professional Cloud Architect. Chris, let's go roll with the next lab. And then after that, we'll talk about databases and lots of fun stuff to talk about in databases, which are obviously a critical business application in any network, in any data center or cloud architecture. It's all cloud anyway.
Hello. In this lab, I will demonstrate how to host a static web page using Google Cloud Storage. I will start here in the page cloud.google.com, and I will click from the top menu Docs to open the Google documentation. From the left side menu, I will scroll down, click Storage, scroll down again, click Storage Solutions, and then click Cloud Storage. Here it opens the documentation about cloud storage with some links, some training. We recommend you read the documentation about the products and services you are going to use. I will click Read Product Documentation, and it opens the product overview of cloud storage. Cloud storage is Google's name for the object storage technology. From the left side menu, I will scroll down to work across products, clouds, and platforms. I will click Serve Website Content and then Host a static website. Here is the documentation for hosting a static website. There are some considerations. I'm skipping the text, but you should read the text to understand all aspects of hosting a static website using Google Cloud Storage. Here, under the Upload Your Sites files, it is selected to use client libraries. I will click Console to get the instructions to be used in Google's Cloud Console. And the instructions are to go to the Cloud Storage Buckets page, click the name of the bucket, and from Bucket Details, click Upload Files. But I still don't have a bucket, so I will create my bucket. From the top left menu, I will select Cloud Storage and then Buckets. I can click Create a Bucket here or click Create on the top here. Give a unique name for the bucket. And click Continue. I will select to create this bucket in one region only, just for simplicity, and click Continue. For how to store my data, I will leave selected as the standard. This is about the different tiers for object storage. If you need to learn more about object storage, please refer to the bootcamp or to Google's documentation. I will click Continue. And here, choose how to control access to objects. The Enforce Public Access Prevention on this bucket is selected by default to avoid exposing or making public documents or objects you would not expect them to be public. But for hosting a static website, I need to uncheck this box to allow the bucket and the object to be public. Access control will be uniform, and then I click Continue. And data protection, I will uncheck soft delete as well. Since this is a lab demonstration, I don't need to protect the objects inside my bucket. In a real-life scenario, please verify if you need soft delete on the objects you have inside your bucket. And then I will click Create. Now the bucket is created. I will use the arrow here to go back to the bucket list. And from the three dots on the right, I will click and edit access. Here, the public access shows not public. I will need to add some users and permissions to make this bucket public. I will click Add Principal. And then from new principals field, I will type in all users and select the option that is displayed for me. And from select a rule, I will click or choose cloud storage on the left and scroll down to storage object viewer on the right. I will select this permission and then click save. And I need to confirm to click allow public access to confirm I want to make this bucket public. I have a warning here that the information is out of date. I will click refresh to refresh, and then now the public access section shows public to the internet. I will click the name of my bucket, and now I would click from the Objects tab. I should click Upload to upload the files I want to share on this static website. But I don't have the files yet. So I will bring a text editor, and I will use as the index.html file part of the index.html file I used in a previous lab, which randomizes the background color of the page. In the other lab, that index.html file also displayed the name of the virtual machine and its IP address. But here from inside a bucket, I cannot do that. I will delete this part and just leave the welcome to my custom page. I will save this file as index.html. And I will save this file in my desktop for now. I will also create another file that will be displayed to the user if the web page the user is trying to reach cannot be found. And I will delete the content that was for the index.html file. And I will save this file with a new name, which will be 404.html. So now I have the index.html file. Oops. Let me go back here for the index.html file. I will close this window and I will open it again just to make sure I have the correct index.html file and 404 HTML files. Now that I have the index.html and the 404.html files ready, I will click Upload to upload them to my bucket. Now I have both files in the bucket. I will click the three dots from the index.html file and let me scroll up a little bit. And I can copy the public URL for the index.html file. I will open a new tab, paste the URL for the index.html file, and then what the browser shows is the content of the file, not a rendered web page. When using a Mac OS computer and when editing text or creating HTML file using the text edit application in Mac OS, some metadata may be included with the file. I will open the index.html file in Visual Studio Code, and then we can compare what should be inside the file, index.html, and what the Visual Studio Code shows is inside the file. So the text edit application adds a lot of metadata that should not be there in the file. I will open the 404 HTML file as well, and this is not what should be in the file. I will bring what should be the content of the file here from the external source and paste it here at the bottom just for a comparison. This is what should be the content of the 404 minimal HTML file that I created, and not all this. I will delete everything here on the top, leaving only what should be inside the file. I'll save the file and do the same for the index.html file. I will delete everything here and bring only what should be in the file, which is the same content as I used in the index.html file in a previous lab. This is the content that should be inside the index.html file. I will save the file and then I will remove VS Code from the front here, and I will close this tab, go back to the bucket, select all buckets, delete them, and I'll upload the two files again, the 404 and the index.html files. With the files in the bucket, I will get the public URL for the index.html file. Open a new tab, paste the URL and hit enter, and still it shows the content of the file. As an experiment, I will keep this tab open and bring VS Code again. And now I will duplicate this index.html file, or copy and paste, and rename to, let's say, index-new HTML file. I will remove VS Code, go back to the bucket, upload the index-new HTML file, click open. Since I have a new file that I want to be my static web page, I need to go back to the bucket lists, and from the three dots, edit the website configuration and change here the index.html to index-new HTML file, and click save. And now I will go inside the bucket, get the public URL for my index-new, and then paste in a new tab. So even after I update the file, remove all the metadata that the text edit application included, and uploaded the file again to the bucket, for some reason it could be the browser cache, or it could be something related to the bucket cache. Because when I try to use the new file uploaded, it still doesn't work. But if I change the name of the file, then the file works as expected. Here is the minimum index page that creates a random background color for each refresh of the page. As I use this file from the previous lab, in that lab, The VM underscore name variable contain the name of the virtual machine, and the external IP variable contain the external IP address of the virtual machine. But since now I am using this index HTML in a cloud storage bucket, there is no virtual machine name or external IP address to display here. Now let's try elaborating a little bit this static website. I will go back to the bucket, create a folder named pictures. I will enter the folder, and then I will upload some pictures I have here in this pictures folder. While the files are being created, I will bring VS Code here again, and I will now edit the index.html file, and I will bring a more elaborated HTML file, which I will demonstrate, but I will not explain all and each line of code it has. I will explain the basic idea. So here is the basic HTML metadata, the title that will appear on the tab of the browser when receiving or accessing the static web page. Here some HTML font and text alignment configuration, some styles applied to the file, to the HTML file. And here under the body of the page, there is a bucket name variable or constant. I need to enter the bucket name here. So I will go back to the console, copy the name of the bucket from here, bring VS Code again, replace this with the name of the bucket. The pictures folder is already there, and this is the API URL that will use the variable or constant bucket name to access the pictures folder and get the pictures from. Here there is some code for getting the elements from the pictures folder, identifying each file in there, and then creating a loop to display the pages, the pictures in the web page. Here is the alternative. If there are no pictures to demonstrate or to show, it will show fail to load image. And I will save this index.html file, take VS Code from the site, go back to the bucket where I have the index.html file, and I will delete this index.html file, upload the new index.html file from the desktop, I will go back to the buckets list again to edit the website configuration and bring it back to index.html file again. Save, go in there and get the index.html file public URL. And now paste in a new tab. For some reason, it still shows the content of the old index.html file. So I will go back there and I will rename this index.html file in Visual Studio Code to index pictures or picture gallery. Upload the index picture gallery HTML file and go back to the bucket, edit the website configuration to use the index picture gallery as the main page of the website. I will get the public URL for that index picture gallery and use it in a new tab. Using the public URL in a browser tab will open the static web page and show the pictures that are inside the pictures folder in the bucket. Now that the file is working correctly, I will go back to the documentation. We have already uploaded the files to the bucket. I have already shared the files, making the bucket public. I have assigned the specialty page, the index picture gallery, and the 404.html. And now is the step to set up the load balancer and the SSL certificate. I will set up the load balancer, but I will not create SSL certificates. So the steps to create the load balancer is to go to the load balancing page, click Create Load Balancer, and then select some configurations. Going to the console, I will open the Network Services Load Balancing in a new tab. Switch to that tab. Click Create Load Balancer. And here are the configurations from the documentation to select the application load balancer and click Next. Then select the public-facing external load balancer and click Next. To select best for global workloads and click Next. Select a global external application load balancer and click Next. And then click Configure. It includes adding a name for the load balancer and then configuring the front end. The name of the load balancer, I will make it static website load balancer. And the configuration for the front end, the name will be static website front end. The protocol I will leave as HTTP to not need an SSL certificate. Here for the IP version IPv4 and for the IP address, I will create a new IP address and then reserve a new static IP address for the load balancer. Create IP address, name it static website IPv4. Click Reserve to reserve an external static IP address to be used with the load balancer. Now I can click Done, go to the backend configuration, from the backend services and backend buckets, click Create a backend bucket. Create a backend bucket. The backend bucket name doesn't necessarily need to be the same as the bucket name. So I will add static website bucket or backend. And here I will browse for the bucket, and I select the bucket from this list and click Select. I will uncheck the Enable Cloud CDN option, and then I can click Create. And I can click OK. On the documentation, the next step is to configure routing rules. Routing rules are the components of an external application load balancer's URL map. For this tutorial, you should skip this portion of the load balancer configuration because it is automatically set to use the backends you just configured. So the next step is to review the configuration and click Create. The next step will be to connect a domain to the load balancer. This is another step I will not execute. Creating a domain could be time-consuming and costly. And then the next step will be to test the website. Since I don't have a domain, I will use the reserved IP address to access the website being hosted in the cloud bucket. The static website load balancer is okay. Let's see the backend. That's all right. And now I will open the VPC network IP addresses in a new tab to get the reserved IP address that was created. Here it is. I will copy this IP address, paste in a new tab, and hit enter. This could take some time for the load balancer be active and working. Now, the reserved IP address entered in the web page return the web page showing the pictures from the pictures folder. Reminding everyone, I haven't covered all aspects of hosting a website in an object storage. This is just to demonstrate the functionality. Now I will go to the documentation and execute the next step, which is the cleanup. The first option is to delete the projects. Then everything inside that project would be deleted as well. But I will keep the projects, so I will delete individual services I used in this lab. I will start deleting the load balancer. And then select the load balancer and then click Delete. It offers to delete the backend buckets as well. I will select and click delete to delete the load balancer. After deleting the load balancer, I will delete the static IP address. It's now in use by none. I can select the static IP address and then click Release Static Address and click Release to confirm I want to delete the IP address. The IP address is now deleted. I will go back to the load balancing page. The load balancer is deleted as well. I can go to the bucket page, and then from the bucket list, I select the bucket, and then I click delete. I need to type delete here in this field and press and click the delete button to confirm I want to delete the bucket. Now the bucket is deleted, the load balancer is deleted, and the reserved IP address is deleted. In this lab, I demonstrated how to host a static website from a Google Cloud Storage bucket. I also demonstrated how to clean up and delete all resources used in this lab. Thank you for watching and see you in the next lab.
Okay, well, we are back. We've got about 2 more lectures today that are going to be on databases, which are fun. Did you have any questions on Leo's labs? If you did, just give us a quick question. Leo and I want to check in and make sure you're doing good. If not, we've got 2 lectures, about an hour's worth, and then we will be ready to go. And then we'll have another day tomorrow, and then one more day, and we're probably going to finish on Thursday. So just to remind everybody that we have a completely free study guide. If you just joined us, got notified by YouTube, and just got here for the free Google Professional Cloud Architect training, we've got a completely free study guide. It's about 550 pages to go along with the exam. Completely free. Chris or someone from my team will drop that link into the chat box now. I also want to remind everybody that there is a playlist that if you just got notified and found out about day 7 of the Google Professional Cloud Architect Bootcamp, don't worry. You can go back and watch day 1, 2, 3, 4, 5, and 6 of all the Google Professional Cloud Architect Bootcamp, so you can prepare for that Google Professional Cloud Architect exam and certification. So we've got you covered on there. Tomorrow morning at 11 a.m., I'm going to come out and discuss career questions. You've got a career question in technology, want to become an architect, want to become an engineer, want to become a cloud architect, a security architect. What's the difference between an AI architect and a cloud architect and an enterprise architect? Whatever questions you want, we'll bring them. You want to know how to get your resume to stand out? We'll talk. You want to know which certifications matter? We'll talk. Just bring me your questions and I'll do what I can. That's completely free at 11. And then on Thursday, we run a webinar on how to become an architect. We will go over what you need to do to get an architect job, regardless of your background. It's based upon the system that I built 25 years ago, about teaching you how to be the best 25% in your field, making sure that you have the top 25% of skills, and that will be the business, the technical, but whatever, we'll tell you what those skills are so you can get them everywhere. We'll talk about what are those top 25 certifications that are going to make you stand out. We'll talk about how do you build the brand and show the world that even if you don't have the experience, you're a top 25% contributor. And then we'll talk about all the changes you need to do to get out there as an architect. And you can ask me any questions, and it's all free. So join us. That link, that'll be on Zoom. I'll be speaking to a lot of people on Thursday, like I do every Thursday. All right, give me a hashtag Google Professional Cloud Architect. And then Chris, let's get back into the chat box. Back into the content. Now we're going to discuss databases, and databases are going to be absolutely critical in cloud architecture and definitely a big component of the Google Professional Cloud Architect certification. So what is a database? At a high level, a database is an application that helps us store large amounts of data. And databases facilitate sorting, calculating, reporting, and information sharing. So imagine you just threw all your stuff into a giant box. It'd be pretty hard to get the information out of it. But imagine instead of storing the data in a box, you found a way, or the information in a box, you found a logical way to organize it, categorize it, so you could easily find what you want. Effectively, that's what a database is. And databases are going to be a critical component of modern applications. So we're going to talk about databases. Now, on Google, just like every data center and every other cloud provider, you will have the following types of databases. Some of these are not exactly databases, but we're going to call them databases. You will have relational databases, which are definitely databases. You have NoSQL databases, which are databases. We'll have data warehousing databases, which are databases that are really designed to store huge amounts of information. And with all this information, we can gather some business intelligence and make better business decisions. And then we'll have something called a data lake. And we can walk through each and every one of these examples and when they're used and why they're used. Now, when you are in Google's cloud, you're going to have the same two options of databases you have in every other cloud provider. You can create and manage your own database server. So, for example, you had a database on a virtual machine in your data center, and you just move that virtual image over. That is you in a self-managed database. And when you create a self-managed database, you install your own database, you determine the exact performance capacities of the database you want, and you can manage it. And in this manner, you can have the same database, for example, potentially on 3 different clouds set up identically with identically set up virtual machines that you manage. Imagine Apache Cassandra, for example, which is a NoSQL database that can read and write from all nodes. So guess what? You can stick a couple of them in Amazon, Cisco, Google. They can all synchronize and you manage the virtual machines. Ultimate control. Now, ultimate control means you can do whatever you need, but now you've got the operational overhead of managing these servers and knowing how to scale these servers. And we can talk about how to scale relational databases, but scaling these servers, realistically speaking, can be a bit of a work in databases. Now, Google also offers managed services, and here this provides a lot of flexibility. They help a lot with the scalability for you, and typically with Google, they're compatible with open source databases. There's a very strong integration with Google's managed databases and other Google Analytics and other AI and machine learning tools. And these could be good for cloud native environments where you're trying to reduce the data management overload, or ideally single cloud environments. So we have to think about what's best for us after evaluating the trade-offs, and that's architecture in general. So now let's talk a little more about databases, and they are systems. And that's why you often hear them called DBMS, Database Management Systems. And they are systems for storing, organizing, and managing structured or unstructured data. So depending upon the data we have, we'll determine what kind of a database we need. Depending upon what our goals are, we'll determine what kind of a database we'll be using. Databases can be relational, which are very structured databases. They're rows, columns that look a whole lot like a spreadsheet. Data is related to each other, and we'll talk more about that. Or the databases can be flexible and offer formats like JSON or maybe key value pairs. And flexible schema databases and NoSQL databases are used for different applications. Because their schema is flexible, they can be huge and store ridiculous amounts of information. But because they can be flexible, you typically think of a NoSQL database of saving where you're at in your Netflix movie, or saving where you're at when you pause a video game. Typically that's stored in a NoSQL database. And as a rule, databases handle tasks like transaction management, query or processing, which is asking it information and getting a response back. And databases have to ensure that the data is consistent. Now, relational and NoSQL databases are a little different about this, and we'll talk about that. But keep that in the back of your mind. In Google, they have a service like Cloud SQL, which is a fully managed relational database. while they have Bigtable, which is going to be an option as a NoSQL database. So Google will have their own proprietary databases. Like AWS has DynamoDB as their proprietary NoSQL database. Microsoft has Cosmos DB, which is their proprietary NoSQL database. And Google has Bigtable. So, we can think about what we want to use and when we need to use it. Remember, 98% of organizations are multi-cloud. So we probably, if we needed a NoSQL database, would be better with something like Apache, Cassandra, or MongoDB. And then we could evaluate those based upon our needs, read, write, load kind of thing. Because, for example, Apache Cassandra can write to all nodes, which makes it better for write-heavy activities often. And MongoDB is typically better for read-heavy loads or more mixed loads. So it all depends on the workload that you're actually using and what you're trying to achieve out of it. So we use databases quite frequently because of their ability to store information and for the ability to get it. So let's talk a little bit about relational databases. Relational databases are structured rows and columns, like rows and columns. That's what you got with a relational database. Now, relational databases all use the language structured query language, which means you can basically ask a question in a standard language across all of them, and then you get the information back in much the same way. Relational databases are immediately consistent. They adhere to what you call the acid principle, which means atomicity, or they're atomic. And what it really means is it's all or nothing. You either write it or you don't. The information is consistent, meaning if you've got two read replicas in the database, the second somebody writes something to the database, all nodes are synchronized instantly. And many applications need that. So if you need instant synchronization and consistency of all your data, you're typically using a relational database. So atomic, all or nothing, consistent, everything being the same. Isolated. Now, what does that mean? It means that as soon as you create one transaction in a database, it's completely separate from another transaction. It is isolated. And it is durable, which means it's not going anywhere. Once you put the information in the database, it's supposed to stay there. It needs to be there. So ACID transactions, all or nothing. Information is consistent across all your databases in that system. One transaction doesn't affect another translation. I think that's called isolation. And durability means once you put your information in there, it stays there. So we've got lots of options. Google Cloud SQL provides a fully managed environment for many popular relational databases like MySQL, Postgres, Microsoft SQL servers. So in this case, if it's managed, you can put your systems here and Google handles the heavy work of a lot of the scalability for you. Or you can build your own virtual machines and have ultimate control how you want to scale it. Now, with relational databases, we have read load and we have write load. And I kind of showed you that. So before I get to NoSQL databases, I want to talk a little bit about scalability of these things. So if we have a relational database, what we have to understand is databases are not like other applications. We can't use a load balancer to share amongst the database like we could use others. So what we can't do is this. This is not an option. Now, this is an option for our web servers, but we can't do this. We can't load balance with a load balancer back and forth between. So since we can't do that, we get into challenges of how do we scale these? Now, there are some databases that can write to all nodes, which makes this a whole lot easier. But as a rule, most relational databases can only write to one node. And databases by default have to handle both reading and writing. So what we can do is if this database has to do read and write, we can offload some of the read and some of the write load. So let's say we have a traditional 3-tier environment. And I'm putting this here because you might see a lot of questions about a 3-tier environment on the Google Professional Cloud Architect exam. So in this case, let's say this is a web server. And then say behind the apps, behind the web server, we have an app server. Web server in the 3-tier environment provides the front end that the user experiences. The application servers handle the business logic that's going on. So normally, if we had nothing else, a message would hit the web server. Let's say you've got a user, they log in, the application server runs the business logic, and I bought 100 cans of fancy white albacore tuna for Cindy, and that transaction gets written in the database. And that's how it stays there. So that's pretty normal. Now, what would happen if 100 people decided to buy stuff? They sent it to the application server, and then the database was down. I think that's kind of icky, right? So we'd lose all these orders, and we don't want to lose orders. So typically, one of the ways you can actually reduce write load on a system is with something called a queue. And here's what we do with this. So here's what, in this particular environment, now we have a web server. User goes, buys their thing. Application logic is done. The order is stored in the queue. If the database has capacity to get it, it goes straight into the database. If the database is too busy, it does smooth things down. And why does this matter? Application traffic is not consistent typically. We're going to have ups, we're going to have downs, we're going to have ups, and we're going to have downs. So let's say over here, when things are down, that the CPU is 20%. And let's say when things reach this max capacity, the CPU is 95%, which is a big deal because we might start where we don't have much capacity left. What if instead of going up and down with the queue, we can kind of have the messages coming in like this at an even pace? Because when it comes in real fast, we can just store them in the queue a little longer. And when it comes in slow, that's the time we drain the queue and put it in the database. So we typically use queuing to decouple the architecture, also add to scalability by reducing write load. Now, if we could redirect the reading information directly to offload the reading information from this database, well, sure, that's going to help make it a lot easier. So what we typically do is we put what's called read replicas here. And what the read replica is going to be is it's going to be a identical read-only copy of what's in here. Remember, these things are ACID transactions, meaning they're instantly consistent across these environments. And instead of so now we send the write load directly to the database, and we offload the read load for the most part to the read replicas. Have an SQL query, send it to the read replica. Have to write, smooth it out through the queue, and then write it to the database. But we offload our read replicas here. And typically speaking, we can also put some caching in here as well. So now we have some information that needs to be accessed. The information, if it's in the cache, it'll be answered immediately. If it's a read question or a SQL query and it's not in the cache, it'll go to the read replica and then it'll be stored in the cache. And then the next query will be answered by the cache if it's the same query. So scaling these things is going to take a combination of smoothing out write load with queue, smoothing out read load with a combination of read replicas and the database, and potentially smoothing out write load depending upon the kind of caching you're using on the way into the database. So relational databases have a lot of complexity, but keep that in the back of your mind. Now, when I talk about NoSQL databases, this is a little different. Relational databases are highly structured. And because they're ACID, that immediate consistency, that's a lot of overhead on the systems. When we get to needing something else, Maybe we need a different kind of database, for example. We might need a database that is more flexible, that might be more scalable, that might do things a little different. And that's where we would be using our NoSQL databases. So I want to make sure that's going to be obvious to us, what we're using, when we're using, and why we're using them. But I want to talk a little bit about more of relational databases before we go on to NoSQL databases. I want you to understand that they typically have tables. And that's going to be the primary structure for storing data. And these tables are going to be consisting of rows and columns. Now, each table is going to represent a specific entity, like a customer, order, or a product. Now, each row will be known as a record. And each row in a table typically represents a single instance of an entity. For example, each row in a customer table is going to be a single customer. Now, when it comes to columns, what we're really talking about is a field that's going to represent an attribute of the entity. For example, we may have a customer table that might have columns for a customer ID and a name and an address. And then we're going to have the primary key, which is going to be the unique identifier for each row in a table. So let me kind of show you a little more about what a relational database typically looks like and what it looks like. Bear with me a second, and I'll bring it back to a whiteboard. If we go in this environment, you can see we have a relational database. You can see how they're structured in rows and columns. And you can see that we've got a customer ID, for example, which maybe tells you a lot about us. And then, for example, we've got an order number, for example, and we have got the amount of the order. So we're able to get data that's related to each other. And that's really what we're talking about, is accessing data that's related to each other to give businesses information about things. Maybe the business sees that a 30% discount, we get this much sales. And then the business can actually use it. So when it comes to relational databases, we have something called a foreign key. And that's going to be a field or a collection of fields in a single table that will uniquely identify a row in another table. So we cannot have two different tables, and the foreign key is going to establish the relationship between them. And relationships are typically defined connections between tables, usually through primary keys and foreign keys. And there are lots of types of relationships: one-to-one relationships, one-to-many relationships, and many-to-many relationships. Now, I mentioned earlier with relational databases, we use this standard language. And a standard language that's used by all systems all around the world means it's very easy to use. And that is SQL, or structured query language. And there are going to be commands for querying data, or asking questions about it, updating a record, managing database structures. Now, one of the advantages of relational databases is data integrity. Relational databases force the data to be exact and identical and not change. And so that's going to be really great, accuracy and consistency in our data. Relational databases tend to be fairly flexible. I don't want to say flexible, I mean somewhat flexible, and that you can easily add a table, delete a table, modify something without affecting existing applications. So you've got that kind of flexibility. There's still somewhat structured compared to NoSQL databases, but they're still somewhat flexible, and they provide a lot of flexibility in managing data. Relational databases, while not as scalable as NoSQL databases, can still get very big and can handle large volumes of data and can be scaled vertically, where you add more computing power to the server, and horizontally, where you add more servers like I actually showed you. I just thought it would be easier to show you that first. Relational databases tend to support robust security features, things like user authentication, permissions, data encryption, and there's other things you would want to do in a database to protect who can see what, and from view's perspective to enhance security. And with databases, the data is independent, meaning that a change to a database schema will not affect other data access methods. And that way, applications can evolve independently of the database's structure. So where do we use relational databases architecturally? Pretty much everywhere. We use them in e-commerce to manage product catalogs, customer information, orders, and inventory. We use it in banking to handle, say, transactions, customer accounts, and financial records. We use them in healthcare to store patient records, treatment histories, appointment schedules. We use them in education and manage student information, course enrollments, or academic records. We use relational databases in the government, managing records for citizens, tax information, public services. So these are widely used. So as I mentioned, we have Cloud SQL, which is a managed relational database that supports things like MySQL, Postgres, SQL Server. And we have Cloud Spanner, which is a globally distributed, horizontally scalable, strongly consistent relational database with built-in replication and backup capabilities. This is a Google service. Now let's talk about MySQL first. Why? Because you can use it everywhere. And MySQL is going to be considered one of the most popular relational database systems in the world. It is widely used in web applications, enterprise solutions, because it's fast, it's reliable, and it's easy to use. MySQL is typically free. It's developed and supported by the Oracle Corporation, who's got a lot of experience with databases. So when we think of MySQL, it is a relational database that's designed to store data in tables with rows and columns. So complex queries, complex transactions. It is SQL compliant, meaning you can use the same structured query language for this as you can every other environment. It is ACID compliant. As I mentioned, it ensures that the systems are atomic, all or nothing when they're written, consistent, all the same, instantly, isolated. One transaction doesn't affect another, and durable, meaning the data doesn't go away. And MySQL works on pretty much everything. Linux, Windows, you could even run it on Mac OS if you wanted to. So it runs on everything. Not that you would use Mac OS to host a server in today's world, but MySQL is good from a storage engine perspective. It supports multiple storage engines like InDB, for example, MyISAM, Memory, and others. And they're all going to be optimized for various use cases. From a replication perspective, MySQL provides various replication methods, whether that be the master-slave relationship or a master-master relationship, and group replication. And this way we can use MySQL to ensure high availability and data redundancy. From a scalability perspective, it can handle some fairly large-scale databases and support high concurrency workloads. And it's got some good security features, user authentication, access control, data encryption. So MySQL has been around a while. It's used widely with web applications. It's often a backend for web applications. It's often used for data warehousing, even though Postgres is designed as more of a data warehouse. So data warehousing analytical applications widely used in all kinds of enterprise applications. And in many cases, you'll see embedded applications that often use MySQL because it's got a very small footprint and it's easy to integrate. So one of the advantages of MySQL is it's open source. It's typically free. It's supported by typically the community, and there's lots and lots of documentation on it, and it's easy to use. So let's talk about Postgres. Postgres is a relational database, but it's often used for data warehouse purposes. It's known for its extensibility and its standards compliance. It's widely used in industrial settings, academic settings, all over because of its big feature set and its reliability. Now, Postgres being Postgres SQL is going to be ACID compliant, like we talked about. Again, that means all or nothing transactions, immediately consistent transactions. One transaction is isolated from another, and the transactions are durable. And it's standards compliant. So it adheres very closely to the SQL standard. So it supports most SQL 2011 features. It's fairly extensible. It allows users to create custom data types, operators, and functions. Extensions can add new functionality to the database. It supports a wide variety of data types, things like JSON, XML, and others. So Postgres, again, widely used. One of the features is concurrency control, which means multi-version concurrency control can handle concurrent operations efficiently without locking the database. From a replication perspective, Postgres supports both asynchronous, meaning not real-time, and synchronous, meaning real-time replication, including logical replication. And this gives you a lot of fine-grained control over how the data is going to be replicated. You can actually do a full-text search, and it's got built-in capabilities for a full-text search, and that allows for some fairly powerful search queries across text data. And it has geospatial support, which adds extensive geospatial capabilities, making Postgres often used for graphical information systems. So you see Postgres widely used in web applications. You see it constantly used in data warehousing because of its ability to scale and handle complex queries in very large data sets. So it's often ideal as a data warehouse. Because it has such big, robust processing capabilities, you'll often see Postgres in financial applications. And because Postgres has such good abilities to store large amounts of information and handling very complex queries, you may see it used in scientific research as well. So some advantages here is that it's open source. It's freely available. It's got a strong community for the most part. It's very high performance. It's really good for read and write operations. And there's a lot of optimization you can actually do here. It's got some good security features, lots of authentication, authorization, encryption, and auditing capabilities. And it scales both by adding more capacity and using bigger servers horizontally and vertically. And it can handle very large data sets and high concurrency workloads. You can typically use MariaDB, and MariaDB is made by the same people that initially made MySQL. In fact, MariaDB is a fork of MySQL. And the goal here from MariaDB was to maintain MySQL's performance and functionality while giving it additional features that were more like the bigger databases. So additional features over the MySQL, but it came out of MySQL. So because it came out of MySQL and that it was a fork, it's highly compatible with MySQL, including matching the APIs, commands, and data structure. So it becomes fairly easy to move from MySQL to MariaDB if you wanted to, not that if an organization wanted to. It supports various storage engines like InnoDB, MySam, Area, Column Store, and more. And that way you can use the storage engine that's optimized for your use case. It does offer some performance enhancements to MySQL with things like thread pooling, advanced optimizer, and better replication capabilities. And it's got good security features like the rest of them, encryption, users, roles, enhanced authentication, what have you. So where do you typically see MariaDB used? Well, a whole lot like the other places, often used in web applications, could potentially be used in data warehousing, often used in enterprise applications that require robust and efficient data management, often used in embedded application because it's small. It's a light footprint. It's just like MySQL in many cases. Advantages here is it's open source and it's freely available. Let's talk about Microsoft SQL Server. So Google does offer various flavors of Microsoft SQL Server, and that allows users that have Microsoft-dependent workloads to bring them to the Google Cloud. Now, when we think about Microsoft SQL Server, it has some different clustering and failover options compared to other databases. There are many versions of Microsoft SQL databases, things like Express, Web, Standard, and Enterprise, and you'll have to determine what's right for your client. Now, Microsoft SQL Server is a relational database that was made by Microsoft, and it was designed to store, retrieve, and manage data that's requested by other software applications, which may run on the same computer or across a network. So, think about SQL Server, and it's been known for scalability, security features, and integration with Microsoft products. So if organizations have a lot of Microsoft workloads and a lot of Microsoft integrations, Microsoft SQL Server is something that is a good option for them because the integration is so smooth. Now, it's a relational database engine that supports tables and rows. It has something called TSQL or Transact SQL, which is an extension of the SQL capabilities that are there. It provides some additional procedural programming capabilities. SQL Server has a whole lot of high availability options like always-on availability groups, database mirroring, even lob shipping. So that can enhance the scalability of the environment and the availability and the ability for disaster recovery. And it integrates very nicely with Microsoft security things. So Active Directory, we've got role-level security, dynamic data masking, which is very good because you may not want to present all data to all users. And it integrates with AD, Microsoft AD, which is the Microsoft IAM platform that's used by so many people. So typically features and integration services which is a platform for data integration and workflow applications. Microsoft SQL Server has a reporting service, a server-based environment to create reports of the software system. It's got an analysis system that can provide online analytical processing and data mining type functionality. So you may see Microsoft SQL Server used in enterprise applications, especially those that need a lot of robust data management like data masking, so not all people can see all information. It's pretty comprehensive from a data warehouse perspective as well. It includes, say, ETL processes and analytical tools and things. ETL, like extract, load, and transfer, to take information from one database and move it to another, what have you. Microsoft SQL Server tends to integrate very nicely with business intelligence tools, especially Power BI, because it's made by Microsoft, so simple to use that tool with Microsoft. And because it's a Microsoft product, it's commonly used as a backend database for Microsoft-type applications, things, say, built on the .NET framework. Could be used for financial applications because it's got very strong transactional support and a lot of security features. The thing here is we often use SQL Server because of the whole Microsoft ecosystem, Windows Server, Active Directory, Power BI, Azure products, for example. It performs typically very well. It has things like in-memory processing, query optimization, parallel processing. It tends to scale very well, especially with large volumes of data and high concurrency workloads. And it's fairly secure. And this one has a lot of data masking and data privacy tools. And it has a lot of management tools that come with it. So that's the key: SQL Server Management Studio, SQL Server Data Tools, and Azure Data Studio. But keep in mind, all these features and functionalities change as providers offer things. So check prior to any architecture if these features are still there. Now I'm going to discuss the Oracle database. And the Oracle database is one of the most popular large-scale relational databases in the world. It has extensive flexibility. It has extensive functionality. It's developed, licensed, and managed by Oracle. Now, there are all kinds of licenses that are out there, like Standard 1, Standard Enterprise. The business has to choose what's right for them. Now, the key to remember is this is a big database. So, very commonly used, extremely powerful multimodal database. Widely used in enterprise environments. It's a commercial database. You're paying for this database and you're getting incredible performance and an extensive feature set. Now, Oracle can also be run in every single cloud that you actually have, again, because it's something you can install on your virtual machines. Now, it is a multimodal database, meaning that it supports relational data functions, document database functions, graph databases, or key value models. So it allows you to store and manage a very diverse set of data. Oracle scales vertically as well as horizontally, so we can deal with tremendous amounts of data. It is very high availability. It features things like real application clusters, Data Guard, Golden Gate, and that can really help ensure high availability and disaster recovery. We've got a lot of performance things we can deal with here. We've got features like automatic storage management, the ability to partition the database, in-memory processing. So we can do a lot that we need to do for high-load, high-performance applications here. So you'll see a lot of the Oracle database. It integrates with a lot of Oracle products, which are also going to be common in businesses. They've got some extensions, something called PLSQL, which is Oracle's proprietary procedural language extensions to SQL. And that enables the creation of very complex queries, stored procedures, triggers, and functions. We have a lot of security, very granular features, encryption, all kinds of auditing fixtures, fine-grained access control, and even a database firewall. So this is going to be a big data with big performance that has features like automatic storage management and partitioning and in-memory processing to really optimize the performance. So big, widely used enterprise database. So where are we going to use this? Any kind of enterprise application you could possibly imagine, especially applications that are going to need a lot of scalability and you need a lot of robust management. Any kind of a data warehouse, we may be using some of these things commonly used in financial services, insurance, and any kind of high volume environment, often used in healthcare, often used in telecommunications because there's a massive amount of data generated in telecommunications. Now we're going to talk about Google's database called Cloud SQL. Now this is going to be a fully managed relational database. And what that means is it's managed by the Google Cloud. So it's going to make database administration much easier. It's going to integrate easily with Compute Engine, Google Kubernetes Engine, and App Engine. It provides a relatively high availability service with 99.95% available. It supports standard SQL queries, and it can be queried directly with BigQuery, which is something we'll talk about later, another service of Google. It gives you deployment options where you choose which one you want: SQL Server, Postgres, MySQL. You can select regions and zones where you want your system to be to minimize latency between your data and your applications. It's got the ability of a high availability configuration in that it provides data redundancy by replicating instances across zones. The primary instance in one zone or data center and a standby instance in another. Data stored in regional persistent disk will be synchronously replicated to both zones, so your data on both databases is consistently and immediately synchronized. And you'll have automatic failover to a standby instance in case there's a primary failure. And we also have the ability to manually fail back to restore data serving from the primary instance if need be. With Cloud SQL, we can use read replicas like I talked about to scale. And we can also use something called sharding. So sharding is distributing data across multiple smaller instances for better scalability and performance. So from a best practice perspective, as Google would recommend, use multiple smaller Cloud SQL instances rather than one big one for efficiency. Okay, we are back. We're back. We've got one more video for the day, and then tomorrow we'll be at the next day. But I think there was one question that came in, so I want to address that in some way, shape, or form, and maybe give you a better answer than you actually hopefully asked, or at least I hope you'll feel that way. And Chris, let's bring in that question. So from In Production, he said, I see I'm talking about relational databases and message queues. By the way, great explanation talking about queues. Thank you. And then you brought in something about Windows Server, about message queues that are specific to some component of Windows servers. So here's what I'm going to do. I'm going to actually talk to you about a few different kinds of queues and how they're actually used in cloud and network architecture for a few minutes, because I think that will really broaden your knowledge on queues, and I think it'll be very helpful to you in your career. The reality is I've never been a sysadmin. I've been an architect my entire life. And the only thing that I really knew about any of the inner workings of Windows was when I did an MCSC, which is in the year 1999, and never worked with a computer in my life. I always worked on networks or architectures, etc. So And when I used a computer, it was to write Word documents, PowerPoint presentations, Excel spreadsheets, Visio diagrams, all things that architects do, and none of the things that they don't do. But let's do this. Let me talk about the kinds of queues and where you would use them, because you're going to see them all over distributed computing and cloud computing. But they're also going to play a very big impact in security if you understand security in your various architectures. So let's kind of walk on that, and maybe I can really help you out, because most people don't understand how they can use queuing to enhance security, and how some of us in networks, a lot of us architects have been doing it for decades. So let's play with this for a few minutes. Let's talk about really where you're using a queue. You should get this to the proper size for the screen. So you use a queue or any time in life where you want to get things into a constrained space. So for example, you've got an airplane that's boarding over here. You've got a single airplane door over here. And if you were in the UK, they would say, please form a queue. And the queue would form, or that would form, and people would wait in the queue. And as people would board the plane, the queue over here would be drained, and the next person from here to here would move forward. And that's queuing that's typically used in airports. It's also used in amusement parks when they calculate lines and weights and other things. But understand that's a basis of a queue. So we're going to be using it in two spaces. Where I'm going to address the software side of it, and then I'm going to address the network side of it. On the software side of it is we could have this microservice-based architecture where we're going to have something that's going to store messages between these services. So we could potentially put a queue here, and we put a message into this queue, and it gets drained and placed into the next service. So you'll typically see that in microservice or distributed applications, lots of these message queues. You're also going to typically see them in that 3-tier web environment that's very commercial, where you've got the web tier, which is the presentation, what you see. And then you have your app tier coming in, coming this way. Now, this is what the user sees. You've got the app tier that's running the business logic. And then behind that, you store the transactions somewhere, which is typically in a database. And usually you put a queue over here so you don't lose messages on the way to the database. That's typically where you put your queue. Now, that's where normal people think about it, but I want to talk to you about how we networking people use queuing. So understand there will always be a constraint. I don't care what you have. I don't care how good you think it is. Something is always going to go wrong. So if we look at this environment, let's say this is a 100 gig network link. This looks like a big, powerful link, right? Well, it could be. It could be filled like nothing. So I want you to take this environment, and let's, for argument's sake, I'm going to get rid of the fill for a second. Let's go back to that. I want you to be able to see the speed of the link. It's 100 gig. Now, let's say this is a link between two switches in a data center. We can have even these two of these bundled together. It doesn't matter. And let's assume that plugged into these switches are big servers. Each one of these servers are like these new AMD EPYC 384 core physical servers, 8 terabytes of DRAM, NVMe RAID arrays, and they've got 100 gig Ethernet connections to the switch. Got the same thing on both sides. Let me just copy this to the other side. And then I want you to see how we use this for security, as well as making sure that we can use a queuing mechanism to make sure that we meet the performance needs of our systems. And this is one of the things that you lose in the public cloud, but this is also one of the things you can do in your private cloud. And since every architecture now is a hybrid architecture, with most of the investment actually going into private cloud money right now, it looks like you're going to see a lot more of this. So where did we go? If any one of these servers here, any one of these can generate 100 gig of traffic at one time, and they can, what happens if this server speaks the bottom one to the other bottom one at 100%? The link is filled, and you know what that means? That means this server, this next server up top, and this other server over here, not a single one of them will have any capacity because the bottom server could take it all. So normally we didn't used to worry about this, because how do you fill 100 gig links when the reality is these servers can go 100 gigs, but their chances are they're not doing more than 10 gigs. So you don't have to worry about it. And you know what? All that seemed fine. In fact, I had a very large voice over IP client, very big bank. And I remember we said to them that you have to run quality of service on your links. And their perspective was, these are the biggest, baddest links in the entire world. We don't have to run quality of service on it. And I'll tell you what happened. What happened is we had some systems on the system that got infected with the worm. The worm caused these systems to propagate as much traffic as they possibly could. They filled up the entire link, and the voice systems and all the technology systems went down. Now, what could have prevented that, and what do we now do in pretty much any architecture that involves any security? We take and prioritize first. In our queue, we create a little queue, and let me show you how we would drain the queue. So the first thing is we mark critical. And we determine what this is, and our network architects help plan this, but they will say, this is priority traffic. Now, there's a lot of these algorithms. I'm going to describe priority queuing, but there's priority queuing, weighted fair queuing, there's low latency queuing. There's all kinds of queuing options and queuing theory out there. But let's say we say that the priority traffic gets 50%. Because in case of emergency, these two top servers of this most priority traffic, and I'll mark the priority traffic in red so it'll make sense. All the priority will be red. Priority traffic can have access to upwards of 50% of this link if it needs it. If it doesn't need it, it's not going to use it. But if there's constraints going into the system, and that means coming into over here, the priority traffic will get 50%. I can then say that all normal traffic over here, we'll mark this. Let's just say we'll call it yellow. Looks like a nice color. We'll call it normal traffic. And you can see the normal traffic, and the normal traffic gets 40%. Now, if there's no constraints, this normal traffic can get as much as it wants. But if there's constraints on the link, the normal traffic is limited to 40%. And now let's look at it this way. Now we've got unknown traffic. And we can't block necessary traffic because we're going to have traffic on our link that's going to be different and we don't necessarily know what it is, or in all cases. But let's say we take unknown traffic and we keep it to 10%. Now, in the event our systems get hit by some wild kind of crazy DDoS attack, all of our other systems, and at least in these cases on that network link, are still good upwards of 90%. We're not taking down or losing the entire link. So you can see how queues could be made to preserve a link or guarantee that your mandatory traffic goes through a link. You can see how they're used in a messaging system in between various microservices, and I showed you how they were done in a 3-tier architecture. So couldn't quite answer your question on the Windows system sysadmin side because I only know architecture, but hopefully that gave you an example of various kind of queues and how they're used in cloud computing and cloud architecture, network architecture, and security architecture. So if you enjoyed that demo on queuing, give me a hashtag Q. QUEUE, and I only know this because I had to put queuing lists on Cisco routers for the short period of time that I did my CCA exam, and then I always spelled it wrong, so it's QUEUE, so give me a hashtag Q. And then, Chris, let's get into that last video that we're going to talk about in this database kind of context. We'll finish up for today, and then we'll have more of the CIS's, I'm going to say the Google Professional Cloud Architect Bootcamp tomorrow. So let's go roll with the content, Chris.
Now we're going to discuss NoSQL databases, or not only SQL.
So NoSQL databases are not relational databases, and they're often known as non-relational databases, but they are designed to be more flexible and handle an incredibly large amount of data. And often with NoSQL databases, they're optimized for a specific kind of a data model, depending upon that type of NoSQL database you choose. The key here to think about with NoSQL databases is they're very flexible in their schemas, which means you can use them for a lot of different kinds of things. And they can handle a huge amount of unstructured, semi-structured, or structured data for the most part. So we're talking about a database that can typically scale and typically scale well. Now, there are many options in the NoSQL database world. For example, we have Apache Cassandra, we have MongoDB, and these are two big, great NoSQL databases that you can use in all of your clouds. But this is a Google certification exam, and in the Google certification exam, they test you on Google products. So we're going to go over the Google products here. We're going to talk about Google Cloud Bigtable, which is the Google supported, Google managed, low latency, high throughput NoSQL database, and it's designed for large analytical workloads. So if you would think about the AWS DynamoDB or Microsoft Cosmos, these are proprietary NoSQL databases made by the cloud vendors, which means that they're not going to work across your clouds. So keep that in the back of your mind. Now, we'll also talk about Google Cloud Firestore. Now, we're going to discuss databases, and databases are going to be Now, we're going to discuss NoSQL databases, or not only SQL. So NoSQL databases are not relational databases, and they're often known as non-relational databases, but they are designed to be more flexible and handle an incredibly large amount of data. And often with NoSQL databases, they're optimized for a specific kind of a data model, depending upon that type of NoSQL database you choose. The key here to think about with NoSQL databases is they're very flexible in their schemas, which means you can use them for a lot of different kinds of things. And they can handle a huge amount of unstructured, semi-structured, or structured data for the most part. So we're talking about a database that can typically scale and typically scale well. Now, there are many options in the NoSQL database world. For example, we have Apache Cassandra, we have MongoDB, and these are two big, great NoSQL databases that you can use in all of your clouds. But this is a Google certification exam, and in the Google certification exam, they test you on Google products. So we're going to go over the Google products here. We're going to talk about Google Cloud Bigtable, which is the Google supported, Google managed, low latency, high throughput NoSQL database, and it's designed for large analytical workloads. So if you would think about the AWS DynamoDB or Microsoft Cosmos, these are proprietary NoSQL databases made by the cloud vendors, which means that they're not going to work across your clouds. So keep that in the back of your mind. Now, we'll also talk about Google Cloud Firestore, which is going to be a serverless, document-oriented NoSQL database that's going to support real-time updates and offline synchronization. We'll talk about Firebase real-time database, and that's a NoSQL cloud database that allows for real-time data synchronization across clients. And we'll also discuss Cloud Memory Store. And that's a managed in-memory data store built on either Redis or Memcached. And we talked about that being used for caching and reducing the workload on the database and increasing performance and scalability. So NoSQL databases can store data without requiring a hard schema. So because of that, the next time you watch a Netflix movie, for example, and you end up at the same place each time, they typically design that with a NoSQL database, for example. Or where you're at in the middle of your video game, that's typically in a NoSQL database because this flexibility of the schema. So the data can be the data and its structures can be modified fairly easily, or at least the data structures can be modified easily. Now, when we talk about scalability in NoSQL databases, These things are often designed to scale out horizontally, and they might distribute load across servers. For example, Apache Cassandra can write across all nodes. So, and obviously read across all nodes. So, because of this, the way these work, they typically scale, and they scale very, very well. So big, high traffic, high volume applications. Now we'll talk about the concept of various data models. So there are a lot of NoSQL databases. We have key value and column friendly types. We have document databases, graph databases, and all of these are types of NoSQL databases, but they're suited for different applications. So in the architecture, you'll have to determine what kind of a database is going to best meet your needs. And ideally, it's something open standard that can run on all your clouds, given that 98% of organizations are multi-cloud, which makes, in many cases, these cloud proprietary databases unusable. So kind of think about that. So we have this concept of consistency, availability, and partition tolerance. So when we're dealing with a NoSQL database, we can choose, they typically prioritize 2 or 3 out of them, or one of the concepts out of them. So by doing so, they're able to scale in the way you want it because they're flexible. If we have to be rigid about everything, that's when things tend to not scale and scale as well. So we have document store databases, typed in NoSQL databases, and they store data such as JSON or BSON or XML templates. And each document in there can contain nested structures in different fields. For example, MongoDB or CouchDB. And often these are used in content management systems, user profiles, catalogs, those types of things, and many others. We also have key value stores. And these type of databases store data as a key value pair, where each key is unique, and that's going to map to a specific value. Think Redis, for example. And this is often used for caching or session management or real-time analytics. And a lot of different uses. Now, we also have column-friendly stores. And these types of NoSQL databases store data in columns rather than rows. And that allows for some fairly efficient storage and retrieval of very large data sets. Here, you're typically thinking of Apache Cassandra or AceBase. You're often using it for time series data or big data analytics or data warehousing. Now, we also have graph databases, and these databases typically store data in nodes and edges and properties that represents the transverse relationships between the data. So you can think of, say, Neo4j or Spanner Graph. And these are often used in social networks, recommendation engines, and fraud detection. So to remind you, what we're dealing with these NoSQL databases is scalability, because they can become very huge. Flexibility, and that they give us a lot of flexibility in the schema. Performance, these are high performance, very fast databases designed for a whole lot of scalability. And we've got a diverse data model, so we can support various data models. And that gives developers the ability to choose between what's going to be the best fit, as well as their applications and the business's unique needs. So you'll see a lot of NoSQL databases in big data, maybe handling large volumes of IoT devices or social media or other environments. You'll see a lot of NoSQL databases in real-time applications. Think like online gaming and often chat applications, any kind of thing that's going to support real time. You'll often see NoSQL databases in the back end for content management. Maybe it's containing unstructured content like a blog or an article or some other multimedia environment. Often use it in e-commerce, such as a product catalog or customer data or order histories, because it can handle several different types of information. Often in social networks, interactions, recommendations between users. So there's a lot of it. So if we look at it and compare and contrast the relational database and the NoSQL database, the relational databases or the SQL databases of a very fixed schema requiring predefined tables and columns. Very, very structured. NoSQL, flexible schema, which gives you the ability to allow for dynamic data structures. NoSQL typically grows horizontally by adding more servers, typically. With relational database, we typically have to go vertically, get a bigger server, and then offload that server to scale with things like read replicas, caching, and queuing, those types of things. Not that we might not want to use queuing with a NoSQL database as well, because queuing is always good because it decouples your architecture and gives you a place to store messages should your database go down, for example. So relational databases enforce that ACID property we talked about, the atomic property, which is it either happens or it didn't, that all or nothing. That the data is immediately consistent wherever you retrieve it in the environment. That one translation doesn't affect it, or one transaction doesn't affect another transaction, which they call isolation. And durability means once you store it, it's there. Now, when we're dealing with a NoSQL database, we often prioritize availability and partition tolerance over strict consistency, meaning we may write something to a NoSQL database and maybe the databases aren't synchronized for a second or two. Whereas with a relational database, it's instant. But that second or two typically allows for a lot more scalability. Relational SQL databases have strong support for complex queries, joins, and aggregations. Now, when we're dealing with NoSQL, we've got limited support for complex queries and joins. They're just designed differently. Now, the next Google service we're going to discuss is Dataproc, or Cloud Dataproc. And what that really is a very huge, large-scale data processing, data analytics, big data kind of tool. And it does things like extract, transform, and load information from one database to put it into another database. It can be used with the creation of data lakes. So it's a big data tool. And the key with Cloud Dataproc is it's a fully managed data processing solution. And it provides it's a fully managed platform that gives you access to things like Apache Spark, Apache Hadoop, or Presto, and other open source big data tools. So it uses open source tools. It's designed for data and analytics processing, and that helps users build these clusters of things very easily. Now, it's a fully managed service, which means you pay as you use it, so it offers per second billing. So it theoretically is a cost-effective solution to temporarily use a bunch of compute capacity to do whatever you need, ETL-wise, extract, translate, load, that kind of thing. And then when you're done with it, you just shut it off. And there's no servers and things for you to really think about the complexity of managing the entire solution. There may be servers, but it's a managed solution. So the key here is it's got an automated cluster management. Normally with these tools, you're going to have a cluster of servers, for example. And with regards to Dataproc, it's automatically going to do that for you. So it'll deploy your cluster. It'll keep logs for you. It'll monitor the cluster as well as management tests. It takes care of that because it's a managed service. So the users can focus more on their data as opposed to all the things necessary to be able to make sure the data is great just to be able to use the data in the first place. So Dataproc, think big data processing workloads, think data lakes, ETL tools, machine learning, large-scale batch processing. So, we want to think about security when we're working with these tools. When we work with Hadoop or Spark, you often need to use web instances for, say, cluster management. And that means we have to be very careful with firewall rules. Because if we expose too much in order to make that happen, we can basically open our networks and create severe security vulnerabilities. And that could get us hacked or cause all kinds of problems. So we have to be careful how we do it. Anytime we deal with things, we need to make sure our connections are secure. So using things like whether it's an SSL tunnel or something to that effect to avoid exposing the data on the open internet. Because big data, we don't want it on the internet. So let's talk a little bit about Cloud Dataflow. Now, that's going to be a fully managed serverless data processing tool. Cloud Dataflow, again, is serverless, so you don't have to think about servers to manage clusters. And it enables users to easily focus on building data pipelines. And we have this concept that we can do unified stream and batch processing with this tool because data flow supports both streaming data processing and batch data processing. So anytime we can deal with streaming data processing, especially as we can get to real time, it gives the businesses immediate insight into what's going on, and then the businesses can then make changes in real time related to the data that's coming in. Better business decisions means better outcomes. So these tools, when applied properly, can provide a lot of business value. Okay, so we've introduced some of the Google tools now, and I mentioned NoSQL databases and talked a bit about them. So now let's talk about Cloud Bigtable. Now that is the Google proprietary NoSQL database that they own. And it is designed for very large-scale analytical and operational workloads, just like every other NoSQL database. It's designed to handle an incredible number of requests per second with very low latency. And, this is suitable for things like a personalization engine, maybe some digital media, IoT, and any other kind of large-scale data application you could possibly think of. So it's going to seamlessly connect with other Google Cloud services. Think like the BigQuery, which is Google's proprietary data warehouse solution, or an Apache ecosystem of tools like HBase, for example. So we can think about the NoSQL databases, and Google's version is just Cloud Bigtable. Now, it's a fairly high availability service, depending upon how it's deployed. They say 4 nines availability. It can scale to billions of rows and thousands of columns and petabytes of data. So we're talking huge database here. And Google has a lot of experience with big data. I mean, if we think about all the algorithms they've had and all the users they've had, Google themselves has a tremendous amount of experience with big data. Being the largest search engine with Google, the second largest search engine in the world, which is YouTube, lots and lots of algorithms, and algorithms are based upon data. So, we can think of this, of what we're dealing with here is big, big environment. Now, it can extend to multiple client libraries like Apache HBase for Java. So, got a lot of flexibility for developers here. And it can be used for mapping and reduction operations, stream processing, analytics, that type of thing. So a lot of uses here. So let's talk about some common use cases with Cloud Bigtable. One is time series data. So it's ideal for storing and querying some time series data sets. Marketing data, effective for personalization and recommendation systems. So a lot of opportunities there. Financial data. In finance, we have a huge amount of things that are stored. Great options. Huge scalability needed there. IoT devices, all these little devices out there, for example. Vast amount of information could be generated. Graph data, so it's going to support querying and analyzing graph data sets. So these are designed for high throughput, for example. High throughput analytics. Big, big performance. Now, I introduced Cloud Firestore before, but we're going to talk about it a little more now and a little deeper now that you know what they are. And Cloud Firestore is a fully managed NoSQL document database. So fully managed, serverless, cloud native, and it's designed for modern mobile, web, and IoT applications. It's designed for speed, and it's designed for scalability. Now, it's a successor to Datastore. FileStore is kind of Google's next generation of FileStore, and it improves its capabilities and scalability. Now, when we're dealing with Cloud Firestore, we can get to some pretty good levels of availability as well. They say 99.99%, and this is ideal for user profiles, for example, because it can store and manage dynamic user profile information very efficiently. These are perfect for product catalogs that are suitable for maintaining and querying large product databases. They're great for storing where you're at in, say, a video game, and enabling real-time updates and synchronization across devices. But remember, this is Google proprietary. So maybe you can or can't use something like this depending upon how many clouds you're going to be in. So Cloud Firestore is designed for global scale, and it's going to support applications with users globally. And that way we've got some kind of seamless data and real-time collaboration, which means people working together across the world. So that improves efficiency for business, potentially creativity in the development of new things. And Cloud File Store provides some good real-time synchronization, and it offers strong real-time synchronization. And that means it's an excellent choice for our applications that need to reflect changes instantly across clients. So you have the ability to be very consistent with this. It's serverless, so that means there's nothing to manage infrastructure-wise. So the people that are using the systems can focus more on what they're going to use the data for, as opposed to worrying about the application, the servers, what have you. File Store is widely used in mobile applications, web apps, IoT platforms where scale and real-time data handling is required. Okay, we're going to discuss another NoSQL database. And of course, this is also Google proprietary. And that's going to be Cloud Memory Store. And that's going to be a fully managed in-memory service database. So Cloud Memory Store is going to be a managed Redis or service for Redis. You could use it for memcached as well. But it's designed for very fast sub-millisecond access. And it's designed to be scalable and high availability. Memory Store is going to be scalable, and it's going to offer at least 99.9% availability, and it can go up to 99.999% if you use 3 or more regions in the Google Cloud. So it's a possibility. So it's very compatible with open source tools like Redis and memcached, so it's going to be fairly easy to integrate into applications without needing to make any code changes. So where might you use this? You may use Memory Store for building application caches. The goal here is to speed up data retrieval by storing frequently accessed data in DRAM or memory as opposed to storage, especially since block storage, which is what we typically use in the cloud, is still relatively slow. So if we need to speed it up, we can use a cache. And we get very good metrics out of Cloud Memory Store, which means we can optimize and tune. So lots of metrics, dynamic scaling of the instances, and that way it can optimize the cache hit ratio. And we'll recall we talked about caches where we said the cache hit is when the cache had the information and responded, and the cache miss is when we had to go to the cache, didn't have it, and we went back to the source, and it was stored in the cache. So we can really do a lot to improve performance with those. But the key here is going to be fast data access, so sub-millisecond latency. So if you've got a performance-driven application where real-time access to data is needed, that's going to be a good thing. And it's a relatively simple migration because it's compatible with Redis and memcached, which are the 2 caches you're probably already using. So it doesn't need a lot of adjustments. Now, Cloud Memory Store is often used in application caching to store frequently accessed information, session storage for user session management, especially for high traffic applications, real-time analytics where we've got quick data retrieval for real-time analytics, potentially even there's some security monitoring as well to ensure that the data is securely managed with built-in monitoring that keeps track of system health. All right, we are back. That was the last video for the day. You had some labs from Leo. You had some lectures from me, some little whiteboarding sessions. So that is our plans for today. Now, tomorrow, we've got some fun things. We'll cover data warehousing. We will cover encryption. We will get into monitoring, logging, and some DevOps kind of concepts. So we've got lots of fun planned for tomorrow. And as it's tracking now, we should be finished, hopefully, on Thursday night and give everybody a Friday off because we've been going pretty hard now. You guys have been working really hard. So congratulate yourselves for sticking with us through this Google Professional Cloud Architect Bootcamp. So, Leo, do you have anything to say about tomorrow?
Yes, Mike. Tomorrow we have a demonstration of the PubSub, which is the event-driven service from Google Cloud.
PubSub, that sounds kind of fun. So that's what Leo's got some labs on. We've got other things to talk about tomorrow. You know, maybe if you had a good time today, maybe like the video or subscribe to our channel and hit the bell to be notified of new things. I almost always come live on Tuesday to answer cloud and networking and AI and security architect career questions. And tomorrow, even though we're doing the bootcamp at the normal time, I'll be here at 11 a.m. And join me on Thursday for How to Become an Architect webinar. We run one every week. Love to see you. Love to talk to you on Zoom. Love to hear about your goals and basically talk about what we do as architects, the skills you need as architects, the struggles people get when finding architect jobs when it's relatively easy if you know how and what you're supposed to do. And we're going to talk about all of it and potentially even how to see the hiring manager. It's all free. Sign up. The link is in the description below. So have a great day, everybody. We will see you tomorrow, and maybe give us a hashtag Google Professional Cloud Architect too. Take care.